Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the deepest mystery that has ever puzzled human minds, the true nature of galaxies themselves, and how we spent centuries staring directly at entire universes without recognizing what lay before our eyes. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The year moves through 1845, and William Parsons, the third Earl of Ross, adjusts the massive mirrors of his 6-foot reflecting telescope in the damp Irish countryside. His instrument represents the largest telescope on Earth, its metal surfaces polished to perfection by craftsmen who understand that starlight travels unimaginable distances only to be captured or lost by the quality of human metalwork. Through the eyepiece, Parsons observes a peculiar patch of light in the constellation Canes Venatici, a fuzzy, elongated glow that previous astronomers have catalogued simply as Nebula number 51 in Charles Messier's list of celestial nuisances. But tonight, with atmospheric conditions unusually steady and his mirrors perfectly aligned, Parsons sees something that stops his methodical observations entirely. The nebula glow resolves into structure, delicate, spiraling arms that curve outward from a bright central hub like cosmic pinwheels frozen in space. He sketches what he observes with careful accuracy, his drawings capturing spiral patterns so intricate and regular that they seem almost engineered rather than natural. These spiral nebulae, as they come to be known, dot the sky in every direction, each one a perfect whirl of light spinning in the cosmic deep. Yet despite their beauty and geometric precision, no astronomer of Parsons' era can explain what these objects actually represent. The prevailing assumption, reasonable given the tools and knowledge of the time, places them firmly within the boundaries of our own stellar system. They must be clouds of glowing gas, perhaps stellar nurseries where new suns condense from cosmic vapor, or possibly the remnants of ancient stellar explosions still cooling in the interstellar medium. After all, the entire observable universe consists of the Milky Way, that river of stars stretching across Earth's night sky, and surely nothing exists beyond its boundaries except empty space extending toward infinity. This assumption rests on careful reasoning. Telescopes reveal that spiral nebulae appear small and faint compared to individual stars, suggesting they occupy modest volumes of space within our local cosmic neighborhood. Their spiral structure resembles atmospheric phenomena, hurricanes seen from above, whirlpools in terrestrial waters, or the rotation of fluid dynamics that might govern gaseous matter subject to gravitational forces. The mathematics of the era, while sophisticated enough to predict planetary orbits and tidal forces, cannot yet conceive of gravitational systems large enough to organize billions of stars into coherent rotating structures. More puzzling still, some spiral nebulae appear to contain what look like individual stars scattered throughout their glowing arms. These stellar points of light seem impossibly faint and numerous, as if viewed from tremendous distances. Yet such distances would place the nebulae far beyond the accepted boundaries of creation itself. The logical conclusion, reached by virtually every astronomer who studies these objects, explains them as relatively nearby clouds of luminous gas mixed with small, dim stars, perhaps the remnants of stellar formation processes still poorly understood. Only a few observers notice subtle details that refuse to fit this comfortable explanation. The spiral patterns themselves seem too perfect and persistent for mere gas clouds subject to turbulent motion. Fluid dynamics suggests that any spiral structure in a gaseous medium should dissipate within relatively short astronomical timescales. Yet these cosmic pinwheels maintain their crisp geometry across decades of observation. Their light, when analyzed through the primitive spectroscopes of the mid-19th century, sometimes shows characteristics that seem inconsistent with glowing hydrogen or other common stellar gases. More mysteriously, spiral nebulae avoid the plane of the Milky Way almost entirely, clustering instead toward the galactic poles where dust and stellar obscuration thin to transparency. This distribution pattern puzzles astronomers who expect cosmic phenomena to follow the gravitational architecture of our stellar system. Gas clouds and stellar nurseries should concentrate along the Milky Way's central plane, where stellar density reaches its maximum and gravitational forces create the conditions necessary for continued star formation. Yet spiral nebulae seem to prefer the cosmic suburbs, scattered across regions of space where stellar density drops to its minimum values. The mystery deepens when astronomers attempt to measure the distances to these objects using the standard techniques of their era, trigonometric parallax, which reveals stellar distances through Earth's annual motion around the Sun, fails completely for spiral nebulae. They show no measurable parallactic shift whatsoever, suggesting distances greater than any known stellar object. Yet such distances would require spiral nebulae to emit energy far beyond anything observed in terrestrial or solar physics. The light output necessary to appear as bright as they do from truly cosmic distances would demand energy sources equivalent to millions of suns burning simultaneously. This energy requirement seems physically impossible given the understanding of stellar mechanics in the 19th century. Stars derive their energy from gravitational contraction, a process that provides sufficient power for thousands or millions of years of steady illumination. But no known physical mechanism can sustain the energy output that spiral nebulae would require if they truly lie at the enormous distances suggested by their lack of measurable parallax. The logical conclusion places them closer to Earth, within the comfortable boundaries of our known stellar neighborhood, where their modest energy requirements can be satisfied by conventional stellar physics. Yet even this conservative interpretation leaves profound questions unanswered. Why do spiral nebulae maintain such perfect geometric structure? What forces organize their matter into such precise patterns? How do they avoid the gravitational influence of the Milky Way's stellar population? And why do they cluster in regions of space seemingly divorced from our galaxy's primary architecture? The astronomers of Parsons' era possess no framework for answering these questions. Their cosmos extends only as far as the most distant observable stars, perhaps a few thousand light-years from Earth to the farthest edge of the Milky Way system. Beyond that boundary lies empty space, cold and dark, extending toward infinity without structure or content. The idea that spiral nebulae might represent separate stellar systems, entire galaxies comparable to our own Milky Way, but located at distances thousands of times greater than any known star, exceeds the conceptual boundaries of 19th century astronomy. So the mystery persists. Quiet and patient, waiting for tools and concepts not yet invented, spiral nebulae continue their slow rotation against the stellar background, their light traveling millions of years to reach telescopes that mistake them for nearby wisps of glowing gas. Each photon carries information about cosmic scales and energy sources that will not be understood for nearly a century. The universe extends far beyond human comprehension, yet reveals its secrets only to observers equipped with sufficient conceptual frameworks to recognize what their instruments actually detect. And in the meantime, throughout the 1840s and beyond, astronomers continue cataloging these enigmatic objects as local phenomena, unaware that they stare directly at entire cosmic cities of stars, islands of creation so distant that their light began its journey toward Earth when life itself was just beginning to stir in terrestrial oceans. The year settles into 1920, and Washington, D.C. experiences an unusually mild April evening as two of astronomy's most distinguished figures prepare for what history will remember as the Great Debate. The National Academy of Sciences has arranged this formal discussion to resolve one of the most pressing questions in cosmic science. Do spiral nebulae represent nearby gas clouds within our own stellar system? Or do they constitute separate island universes, scattered throughout space at distances so vast they challenge every assumption about the scale of creation itself? Harlow Shapley arrives at the Smithsonian's National Museum of Natural History carrying decades of careful observations and mathematical calculations that have revolutionized humanity's understanding of our own galaxy's structure. His work mapping globular star clusters has revealed that the Milky Way extends far beyond previous estimates, perhaps 300,000 light-years from edge to edge, making it an almost incomprehensibly vast stellar system containing hundreds of billions of individual suns. Given this enormous scale, Shapley reasons, spiral nebulae must surely represent minor phenomena within our galaxy's boundaries, rather than separate cosmic entities of comparable magnitude. His confidence rests on more than theoretical speculation. Throughout the previous decade, Shapley has measured distances to globular clusters using Cepheid variable stars, pulsating giants whose rhythmic brightness changes provide reliable indicators of their intrinsic luminosity. By comparing these intrinsic brightnesses with their observed apparent magnitudes, he has mapped the three-dimensional structure of our galaxy's halo system, discovering that Earth occupies a distinctly suburban position far from the galactic center, the Milky Way. According to his measurements, extends roughly 300,000 light-years from rim to rim, 10 times larger than previous estimates suggested. This revised galactic scale creates profound implications for understanding spiral nebulae. If our own stellar system spans such enormous distances and contains such vast stellar populations, then surely it represents the dominant structure in our local cosmic neighborhood. Spiral nebulae, with their modest apparent sizes and relatively faint luminosities, must be minor appendages to this grand galactic architecture, perhaps gas clouds condensing into new stellar systems, or possibly the remnants of ancient stellar explosions still glowing in the interstellar medium. Across the lecture hall, Heber Curtis organizes his own evidence with equal confidence. Though pointing toward precisely the opposite conclusion, his spectroscopic studies of spiral nebulae have revealed characteristics that seem inconsistent with nearby gas clouds, while his observations of novae, stellar explosions that briefly outshine entire star fields, suggest that these events occur at distances far beyond the accepted boundaries of our stellar neighborhood. If spiral nebulae truly lie within the Milky Way, Curtis argues, then the novae observed within them should appear much brighter than those found in our local galactic environment. Curtis has spent years photographing spiral nebulae through the powerful telescopes at Lick Observatory, accumulating evidence that these objects possess characteristics unlike any known gaseous phenomena within our galaxy. Their light curves show stability over decades of observation, suggesting they represent stable stellar systems rather than turbulent gas clouds subject to rapid evolution. Their spectral signatures, while difficult to interpret using the primitive spectroscopic techniques of 1920, sometimes show absorption lines characteristic of stellar atmospheres rather than emission lines expected from glowing hydrogen. More compelling still, Curtis has discovered that novae within spiral nebulae appear systematically fainter than comparable stellar explosions observed within our local galactic neighborhood. This brightness difference suggests enormous distances, far greater than any previously measured astronomical object. If Curtis's distance estimates prove correct, then spiral nebulae must emit total energy outputs equivalent to billions of stars burning simultaneously, energy requirements that seem to exceed any known physical mechanism. The debate unfolds with scholarly politeness, each astronomer presenting evidence accumulated through years of patient telescopic work. Neither man can definitively prove his position using the observational tools available in 1920, yet both argue their cases with the conviction that comes from careful analysis of the best data their era can provide. The cosmic distance scale remains largely unmeasured beyond the nearest stellar neighbors. Stellar energy sources remain mysterious, and the physical mechanisms that might govern spiral structure remain entirely theoretical. Shapley emphasizes the sheer implausibility of Curtis's proposal. If spiral nebulae represent separate galaxies comparable to our own Milky Way, then they must contain billions of stars organized into coherent rotating systems across distances measured in millions of light-years. Such distances would require individual stars within spiral nebulae to be completely undetectable using existing telescopes. Yet some spiral nebulae clearly show what appear to be stellar points of light scattered throughout their glowing arms. These apparent stars, if they exist at the distances Curtis proposes, would need to be hundreds of times more luminous than our own Sun, energy outputs that seem physically impossible given current understanding of stellar mechanics. The mathematical requirements become even more daunting when considering the gravitational forces necessary to maintain spiral structure across such cosmic scales. Spiral nebulae would need to rotate as unified systems to preserve their precise geometric patterns across the millions of years required for light to travel from their distant locations to terrestrial telescopes. This rotation would demand gravitational binding forces strong enough to organize billions of stellar masses into coherent structures. Yet no known physical mechanism can provide such enormous gravitational architecture across the distances Curtis envisions. Furthermore, Shapley notes, the energy problem extends beyond simple stellar luminosity. If spiral nebulae truly represent separate galaxies, then their total energy output must account not only for billions of individual stars, but also for any nebula emission. Stellar formation processes and other energetic phenomena occurring within these systems. The combined energy requirements would exceed anything observed in terrestrial or solar physics by factors of millions or billions. No known energy source can sustain such outputs across the cosmic timescales necessary for stable galactic evolution. Curtis counters with observations that seem to demand precisely these impossible scales. The distribution of spiral nebulae across Earth's sky avoids the plane of the Milky Way almost entirely, clustering instead toward the galactic poles, where interstellar dust and stellar obscuration reach their minimum values. This distribution pattern suggests that spiral nebulae exist independently of our galaxy's gravitational architecture, scattered throughout space rather than confined within our local stellar system. Gas clouds and stellar nurseries within the Milky Way should concentrate along the galactic plane, where stellar density and gravitational forces create optimal conditions for continued star formation. The avoidance of the galactic plane represents more than statistical coincidence. If spiral nebulae were truly local phenomena within our galaxy, they should show random distribution across the celestial sphere, with perhaps some concentration toward the galactic center where stellar density reaches its maximum. Instead, their distribution suggests obscuration by dust clouds concentrated along the Milky Way's central plane, dust that would block the light of distant objects while allowing local phenomena to shine through unimpeded. Furthermore, Curtis notes, spectroscopic analysis reveals that spiral nebulae emit light with characteristics subtly different from known gaseous nebulae within our galaxy. Their spectra sometimes show absorption lines suggesting the presence of stellar populations rather than pure gas clouds, while their overall luminosity patterns seem more consistent with integrated starlight than with hydrogen emission from stellar nurseries. These spectroscopic signatures, while not yet fully understood using 1920s analytical techniques, point towards stellar systems rather than gaseous phenomena. The spectroscopic evidence becomes particularly compelling when examining the breadth and complexity of absorption features observed in spiral nebula spectra. Simple gas clouds should show relatively few spectral lines corresponding to hydrogen and helium emission, with perhaps some heavier elements mixed into the glowing medium. Yet spiral nebulae sometimes display absorption spectra with dozens of subtle features suggesting the integrated light of many different stellar types: hot blue giants, cool red stars, and intermediate stellar masses, all contributing their characteristic spectral signatures to the combined light reaching terrestrial telescopes. The novae observations present perhaps the most quantitative evidence for Curtis's position. Within our own galaxy, stellar explosions reach predictable maximum brightness levels that correspond to their distances from Earth through well-established inverse square relationships. Nearby novae appear bright, while more distant explosions within our galaxy appear correspondingly fainter according to mathematical relationships that can be verified through independent distance measurements. Yet novae observed within spiral nebulae appear consistently fainter than their galactic counterparts by factors of hundreds or thousands. If spiral nebulae exist within the Milky Way at distances comparable to known stellar objects, then novae within them should appear as bright as those observed in our local stellar neighborhood. Their dramatically reduced brightness implies distances far beyond the accepted boundaries of our galaxy, distances that would place spiral nebulae in the realm of separate cosmic entities rather than local galactic phenomena. Curtis has catalogued dozens of such novae within various spiral nebulae, finding consistent patterns that suggest systematic distance relationships. The brightest novae within spiral nebulae appear roughly 100 times fainter than comparable stellar explosions within our galaxy, implying distances roughly 10 times greater than the accepted galactic boundaries. Such distances would place spiral nebulae at millions of light-years from Earth, distances that exceed the scale of any previously measured astronomical phenomenon. Yet neither astronomer can provide the definitive measurement that would resolve this fundamental question about cosmic architecture. The cosmic distance scale remains unmapped beyond the nearest stellar neighbors, with reliable distance indicators limited to trigonometric parallax measurements that fail completely for objects beyond a few hundred light-years from Earth. Stellar luminosity standards remain poorly understood, making it impossible to distinguish between intrinsically faint nearby objects and intrinsically bright distant ones without independent distance confirmation. The physical processes governing spiral structure remain entirely theoretical, with no accepted explanation for how gaseous or stellar systems might maintain such precise geometric patterns across astronomical timescales. Fluid dynamics suggests that spiral patterns in gaseous media should dissipate within relatively short periods due to turbulent mixing and differential rotation. Yet, spiral nebulae maintain crisp geometric structure across decades of telescopic observation. The debate concludes without clear resolution, each participant having presented compelling evidence for his position while exposing significant weaknesses in his opponent's arguments. The astronomical community remains divided, some supporting Shapley's conservative interpretation that places spiral nebulae within our own galactic system, others favoring Curtis's revolutionary proposal that spiral nebulae represent separate cosmic entities scattered throughout space at previously unimaginable distances. The division reflects deeper uncertainties about cosmic scales, energy sources, and gravitational architecture that extend far beyond the specific question of spiral nebula distances. Astronomy in 1920 lacks theoretical frameworks for understanding stellar energy production. Galactic dynamics, or the large-scale structure of space itself. These conceptual limitations constrain both observational interpretation and theoretical speculation, leaving fundamental questions about cosmic architecture unresolved until future advances in physics and observational technology. In the months following the debate, both astronomers continue their observational programs, searching for evidence that might definitively resolve the island universe question. Shapley refines his measurements of globular cluster distances, mapping the true scale of our own galaxy with increasing precision while developing improved techniques for measuring stellar luminosities and spectroscopic characteristics. Curtis continues his spectroscopic studies of spiral nebulae, cataloging their peculiar characteristics and searching for stellar signatures that might confirm their extragalactic nature. The astronomical community watches this ongoing investigation with considerable interest, recognizing that the outcome will fundamentally alter humanity's conception of its place within cosmic architecture. Either spiral nebulae represent minor local phenomena within our own stellar system, confirming Earth's position within the dominant cosmic structure of our cosmic neighborhood, or they constitute separate galactic entities that reduce our Milky Way to just one among countless similar systems scattered throughout space at distances that dwarf any previously imagined scale. Yet the answer waits patiently in observational techniques not yet developed and conceptual frameworks not yet imagined. Variable star photometry will soon provide reliable distance indicators for objects far beyond the range of trigonometric parallax, while improved spectroscopic analysis will reveal the stellar nature of spiral nebula populations. The universe extends far beyond the boundaries conceived by either debater, containing billions of galaxies scattered across distances that dwarf even Curtis's bold estimates. The year moves through 1923, and Edwin Powell Hubble adjusts the focus of the 100-inch Hooker telescope atop Mount Wilson, California. This instrument represents the largest and most sophisticated telescope on Earth, its massive mirror gathering light with unprecedented precision from the depths of space. Tonight, atmospheric conditions over the San Gabriel Mountains achieve the exceptional steadiness that allows astronomical photography to reach its theoretical limits, and Hubble prepares to photograph the Andromeda Nebula with exposure times measured in hours rather than minutes. The Andromeda Nebula, catalogued as Messier 31 in the systematic list of fuzzy celestial objects, has puzzled astronomers for decades with its enormous angular size and peculiar spiral structure. Through smaller telescopes, it appears as an elongated patch of soft luminosity spanning several degrees of sky. Larger than many star clusters, yet exhibiting none of the discrete stellar points that characterize true stellar aggregations, its spiral arms, revealed through long photographic exposures, show intricate structure with dark lanes and bright knots that suggest complex internal organization far beyond simple gaseous phenomena. Previous observers have noted what appear to be individual stellar points scattered throughout Andromeda's spiral arms, but these apparent stars remain tantalizingly faint and difficult to study in detail. Their brightnesses lie at the very threshold of photographic detection, making it impossible to determine whether they represent genuine stellar objects within the nebula or merely photographic artifacts created by long exposures and atmospheric turbulence. The question of their true nature holds profound implications for understanding not only Andromeda itself, but the entire cosmic distance scale. Hubble's photographic campaign represents a systematic attempt to push observational techniques to their absolute limits in pursuit of definitive answers about Andromeda's stellar content. Each photographic plate requires exposure times of 3 to 6 hours, during which the telescope must track Earth's rotation with mechanical precision to prevent star images from smearing across the photographic emulsion. The slightest vibration, atmospheric disturbance, or tracking error will blur stellar images beyond useful resolution, making successful photography dependent on exceptional observing conditions and flawless instrumental performance. The photographic plates themselves represent cutting-edge technology, with emulsion sensitivities carefully optimized for astronomical applications. These plates must capture extremely faint light signals while maintaining sufficient dynamic range to record both the bright central regions of Andromeda and the faint stellar points scattered throughout its outer spiral arms. The chemical processing requires precise temperature and timing control to extract maximum information from each exposure while avoiding photographic artifacts that might masquerade as genuine stellar objects. On the night of October 5, 1923, atmospheric conditions achieve unusual stability. and Hubble obtains what will prove to be one of the most historically significant photographs in astronomical history. The exposure, designated H335V by his systematic cataloging system, reveals with unprecedented clarity the northwestern spiral arm of the Andromeda Nebula. When developed and examined under high magnification, this single photographic plate contains information that will fundamentally alter humanity's conception of cosmic architecture. Under careful examination, the plate reveals dozens of stellar points distributed throughout Andromeda's spiral structure. These stars appear sharp and well-defined rather than diffuse, confirming their genuine stellar nature rather than photographic artifacts or gaseous condensations. More significantly, several of these stars show brightness variations when compared with previous photographic plates of the same region, indicating that they belong to the class of variable stars whose light output changes in regular patterns over weeks or months. Among these variables, Hubble identifies one whose light curve exhibits the characteristic pattern of a Cepheid variable star, rapid brightening to maximum luminosity, followed by slower fading back to minimum brightness, repeating with clockwork regularity every 31.4 days. This discovery represents the first confirmed Cepheid variable within any spiral nebula, providing the key measurement necessary to apply Henrietta Leavitt's period luminosity relationship to determine Andromeda's distance. The mathematical calculation that follows this identification proves both straightforward and revolutionary. Using Leavitt's period luminosity relationship, Hubble determines that a Cepheid with a 31.4-day period possesses an intrinsic luminosity roughly 7,000 times greater than our Sun. The observed apparent brightness of this same star, as measured from his photographic plates, appears approximately 16,000 times fainter than the faintest stars visible to the naked eye. Applying the inverse square law that governs light propagation through space, these measurements yield a distance of approximately 900,000 light-years from Earth to the Andromeda Nebula. This distance measurement shatters every previous assumption about cosmic architecture. At 900,000 light-years from Earth, Andromeda lies far beyond the accepted boundaries of our own galaxy, which Harlow Shapley's globular cluster studies had placed at roughly 300,000 light-years in diameter. The measurement definitively establishes Andromeda as a separate stellar system entirely independent of the Milky Way, an island universe, as earlier speculators had proposed, but at distances and scales that exceed even the boldest theoretical predictions. The implications extend far beyond simple distance measurement. If Andromeda represents a separate galaxy at such enormous distances, then its apparent angular size corresponds to physical dimensions comparable to our entire Milky Way system. The stellar points visible within its spiral arms represent individual suns similar to those in our local galactic neighborhood, but located at distances so vast that only the most luminous stellar types remain detectable through existing telescopic techniques. More profound still, Andromeda's total light output, the combined luminosity of all its stellar constituents, must be enormous to appear as bright as it does from such cosmic distances. Simple calculations suggest that Andromeda contains stellar populations comparable to our entire Milky Way, with hundreds of billions of individual stars organized into the spiral structure revealed through telescopic photography. The energy requirements for such total luminosity exceed anything previously contemplated in astronomical physics. The discovery also resolves the long-standing debate about spiral nebula distribution across Earth's sky. If spiral nebulae represent separate galaxies at distances comparable to Andromeda, then their avoidance of the Milky Way's galactic plane results from obscuration by dust clouds concentrated along our galaxy's central disk. Distant galaxies cannot shine through the dust lanes that block their light, explaining why spiral nebulae cluster toward the galactic poles where interstellar obscuration reaches minimum values. Yet Hubble's initial distance measurement contains systematic errors that will require years of additional observation to correct. The period luminosity relationship used for distance calculation depends on calibration measurements of Cepheids within our own galaxy. But these calibration distances themselves remain uncertain due to the technical limitations of early 20th century astrometry. Furthermore, interstellar dust within our own galaxy dims the light of distant objects by amounts that remain poorly quantified, potentially leading to distance overestimates for extragalactic objects. The identification of individual Cepheids within Andromeda also proves technically challenging, requiring multiple photographic plates taken over months of observation to establish reliable light curves for faint variable stars. Atmospheric turbulence, photographic limitations, and tracking errors all contribute noise to the photometric measurements, making it difficult to distinguish genuine stellar variability from instrumental artifacts. Each Cepheid identification requires confirmation through repeated observation and careful comparison with stellar standards of known brightness. Despite these technical challenges, Hubble's discovery provides the first definitive evidence that spiral nebulae represent separate galactic systems rather than local phenomena within our own stellar neighborhood. The cosmic distance scale suddenly expands by factors of hundreds or thousands, revealing a universe populated by countless stellar systems comparable to our own Milky Way. The philosophical implications prove as profound as the scientific ones. Humanity's cosmic environment extends far beyond any previously imagined boundaries. Throughout the autumn of 1923, Hubble continues his photographic survey of Andromeda, identifying additional Cepheid variables and refining his distance measurements through improved photometric techniques. Each new Cepheid provides independent confirmation of Andromeda's extragalactic distance, while also revealing the internal structure and stellar populations of humanity's nearest galactic neighbor. The spiral arms resolve into complex networks of stellar associations, dust lanes, and bright nebula regions that mirror the architectural features observed within our own galaxy. The success of Cepheid distance measurement for Andromeda opens possibilities for extending similar techniques to other spiral nebulae, potentially mapping the three-dimensional distribution of galaxies throughout the observable universe. If most spiral nebulae represent galactic systems at distances comparable to Andromeda, then the cosmos contains millions or billions of separate stellar cities, each one a complete universe in its own right, scattered throughout space at distances that dwarf any previously measured astronomical phenomenon. Yet the technical requirements for detecting Cepheids in more distant spiral nebulae push beyond the capabilities of existing telescopic and photographic technology. Even the powerful 100-inch Hooker telescope can barely resolve individual stars within Andromeda, and more distant galaxies appear as smooth distributions of integrated starlight rather than collections of discrete stellar points. Extending reliable distance measurement beyond the local galactic group will require technological advances in telescope construction, photographic sensitivity, and photometric precision. The universe reveals itself as far grander and more complex than any previous generation could have imagined. Spiral nebulae represent entire cosmic cities of stars, each one containing stellar populations comparable to our own Milky Way, yet scattered throughout space at distances so vast that their individual stars remain barely detectable to the most powerful telescopes available. The cosmic architecture extends across scales that challenge human comprehension, yet yields its secrets to patient observation and careful mathematical analysis. Meanwhile, throughout 1923 and beyond, countless other galaxies continue their slow rotation against the cosmic background, their light traveling millions of years through expanding space to reach telescopes on Earth. Each photon carries information about stellar populations, galactic structure, and cosmic distances that will gradually transform humanity's understanding of its place within the universe. The cosmos waits, vast and patient, revealing its magnificent scale to observers equipped with sufficient technological and conceptual tools to recognize what their instruments actually detect. The year moves through 1923, and Edwin Powell Hubble adjusts the focus of the 100-inch Hooker telescope atop Mount Wilson, California. This instrument represents the largest and most sophisticated telescope on Earth, its massive mirror gathering light with unprecedented precision from the depths of space. Tonight, atmospheric conditions over the San Gabriel Mountains achieve the exceptional steadiness that allows astronomical photography to reach its theoretical limits, and Hubble prepares to photograph the Andromeda Nebula with exposure times measured in hours rather than minutes. The Andromeda Nebula, catalogued as Messier 31 in the systematic list of fuzzy celestial objects, has puzzled astronomers for decades with its enormous angular size and peculiar spiral structure. Through smaller telescopes, it appears as an elongated patch of soft luminosity spanning several degrees of sky. Larger than many star clusters, yet exhibiting none of the discrete stellar points that characterize true stellar aggregations. Its spiral arms, revealed through long photographic exposures, show intricate structure with dark lanes and bright knots that suggest complex internal organization far beyond simple gaseous phenomena. Previous observers have noted what appear to be individual stellar points scattered throughout Andromeda's spiral arms, but these apparent stars remain tantalizingly faint and difficult to study in detail. Their brightnesses lie at the very threshold of photographic detection, making it impossible to determine whether they represent genuine stellar objects within the nebula or merely photographic artifacts created by long exposures and atmospheric turbulence. The question of their true nature holds profound implications for understanding not only Andromeda itself, but the entire cosmic distance scale. Hubble's photographic campaign represents a systematic attempt to push observational techniques to their absolute limits in pursuit of definitive answers about Andromeda's stellar content. Each photographic plate requires exposure times of 3 to 6 hours, during which the telescope must track Earth's rotation with mechanical precision to prevent star images from smearing across the photographic emulsion. The slightest vibration, atmospheric disturbance, or tracking error will blur stellar images beyond useful resolution, making successful photography dependent on exceptional observing conditions and flawless instrumental performance. The photographic plates themselves represent cutting-edge technology, with emulsion sensitivities carefully optimized for astronomical applications. These plates must capture extremely faint light signals while maintaining sufficient dynamic range to record both the bright central regions of Andromeda and the faint stellar points scattered throughout its outer spiral arms. The chemical processing requires precise temperature and timing control to extract maximum information from each exposure while avoiding photographic artifacts that might masquerade as genuine stellar objects. On the night of October 5, 1923, atmospheric conditions achieve unusual stability, and Hubble obtains what will prove to be one of the most historically significant photographs in astronomical history. The exposure, designated H335V by his systematic cataloging system, reveals with unprecedented clarity the northwestern spiral arm of the Andromeda Nebula. When developed and examined under high magnification, this single photographic plate contains information that will fundamentally alter humanity's conception of cosmic architecture. Under careful examination, the plate reveals dozens of stellar points distributed throughout Andromeda's spiral structure. These stars appear sharp and well-defined rather than diffuse, confirming their genuine stellar nature rather than photographic artifacts or gaseous condensations. More significantly, several of these stars show brightness variations when compared with previous photographic plates of the same region, indicating that they belong to the class of variable stars whose light output changes in regular patterns over weeks or months. Among these variables, Hubble identifies one whose light curve exhibits the characteristic pattern of a Cepheid variable star, rapid brightening to maximum luminosity followed by slower fading back to minimum brightness, repeating with clockwork regularity every 31.4 days. This discovery represents the first confirmed Cepheid variable within any spiral nebula, providing the key measurement necessary to apply Henrietta Leavitt's period luminosity relationship to determine Andromeda's distance. The mathematical calculation that follows this identification proves both straightforward and revolutionary. Using Leavitt's period luminosity relationship, Hubble determines that a Cepheid with a 31.4-day period possesses an intrinsic luminosity roughly 7,000 times greater than our Sun. The observed apparent brightness of this same star, as measured from his photographic plates, appears approximately 16,000 times fainter than the faintest stars visible to the naked eye. Applying the inverse square law that governs light propagation through space, these measurements yield a distance of approximately 900,000 light-years from Earth to the Andromeda Nebula. This distance measurement shatters every previous assumption about cosmic architecture. At 900,000 light-years from Earth, Andromeda lies far beyond the accepted boundaries of our own galaxy, which Harlow-Shapley's globular cluster studies had placed at roughly 300,000 light-years in diameter. The measurement definitively establishes Andromeda as a separate stellar system entirely independent of the Milky Way, an island universe as earlier speculators had proposed, but at distances and scales that exceed even the boldest theoretical predictions. The implications extend far beyond simple distance measurement. If Andromeda represents a separate galaxy at such enormous distances, then its apparent angular size corresponds to physical dimensions comparable to our entire Milky Way system. The stellar points visible within its spiral arms represent individual suns similar to those in our local galactic neighborhood, but located at distances so vast that only the most luminous stellar types remain detectable through existing telescopic techniques. More profound still, Andromeda's total light output, the combined luminosity of all its stellar constituents, must be enormous to appear as bright as it does from such cosmic distances. Simple calculations suggest that Andromeda contains stellar populations comparable to our entire Milky Way, with hundreds of billions of individual stars organized into the spiral structure revealed through telescopic photography. The energy requirements for such total luminosity exceed anything previously contemplated in astronomical physics. The discovery also resolves the long-standing debate about spiral nebula distribution across Earth's sky. If spiral nebulae represent separate galaxies at distances comparable to Andromeda, then their avoidance of the Milky Way's galactic plane results from obscuration by dust clouds concentrated along our galaxy's central disk. Distant galaxies cannot shine through the dust lanes that block their light, explaining why spiral nebulae cluster toward the galactic poles where interstellar obscuration reaches minimum values. Yet Hubble's initial distance measurement contains systematic errors that will require years of additional observation to correct. The period luminosity relationship used for distance calculation depends on calibration measurements of Cepheids within our own galaxy. But these calibration distances themselves remain uncertain due to the technical limitations of early 20th century astrometry. Furthermore, interstellar dust within our own galaxy dims the light of distant objects by amounts that remain poorly quantified, potentially leading to distance overestimates for extragalactic objects. The identification of individual Cepheids within Andromeda also proves technically challenging, requiring multiple photographic plates taken over months of observation to establish reliable light curves for faint variable stars. Atmospheric turbulence, photographic limitations, and tracking errors all contribute noise to the photometric measurements, making it difficult to distinguish genuine stellar variability from instrumental artifacts. Each Cepheid identification requires confirmation through repeated observation and careful comparison with stellar standards of known brightness. Despite these technical challenges, Hubble's discovery provides the first definitive evidence that spiral nebulae represent separate galactic systems rather than local phenomena within our own stellar neighborhood. The cosmic distance scale suddenly expands by factors of hundreds or thousands, revealing a universe populated by countless stellar systems comparable to our own Milky Way. The philosophical implications prove as profound as the scientific ones. Humanity's cosmic environment extends far beyond any previously imagined boundaries. Throughout the autumn of 1923, Hubble continues his photographic survey of Andromeda, identifying additional Cepheid variables and refining his distance measurements through improved photometric techniques. Each new Cepheid provides independent confirmation of Andromeda's extragalactic distance, while also revealing the internal structure and stellar populations of humanity's nearest galactic neighbor. The spiral arms resolve into complex networks of stellar associations, dust lanes, and bright nebula regions that mirror the architectural features observed within our own galaxy. The success of Cepheid distance measurement for Andromeda opens possibilities for extending similar techniques to other spiral nebulae, potentially mapping the three-dimensional distribution of galaxies throughout the observable universe. If most spiral nebulae represent galactic systems at distances comparable to Andromeda, then the cosmos contains millions or billions of separate stellar cities, each one a complete universe in its own right, scattered throughout space at distances that dwarf any previously measured astronomical phenomenon. Yet, the technical requirements for detecting Cepheids in more distant spiral nebulae push beyond the capabilities of existing telescopic and photographic technology. Even the powerful 100-inch Hooker telescope can barely resolve individual stars within Andromeda, and more distant galaxies appear as smooth distributions of integrated starlight rather than collections of discrete stellar points. Extending reliable distance measurement beyond the local galactic group will require technological advances in telescope construction, photographic sensitivity, and photometric precision. The universe reveals itself as far grander and more complex than any previous generation could have imagined. Spiral nebulae represent entire cosmic cities of stars, each one containing stellar populations comparable to our own Milky Way, yet scattered throughout space at distances so vast that their individual stars remain barely detectable to the most powerful telescopes available. The cosmic architecture extends across scales that challenge human comprehension, yet yields its secrets to patient observation and careful mathematical analysis. Meanwhile, throughout 1923 and beyond, countless other galaxies continue their slow rotation against the cosmic background, their light traveling millions of years through expanding space to reach telescopes on Earth. Each photon carries information about stellar populations, galactic structure, and cosmic distances that will gradually transform humanity's understanding of its place within the universe. The cosmos waits, vast and patient, revealing its magnificent scale to observers equipped with sufficient technological and conceptual tools to recognize what their instruments actually detect. The year drifts through 1912 and at Lowell Observatory in Flagstaff, Arizona, Vesto Melvin Slipher peers through the eyepiece of the 24-inch refractor telescope with a peculiar sense of unease about what his spectroscopic measurements are revealing. For months, he has been systematically studying the light from spiral nebulae, using a prism to spread their faint glow into rainbow spectra that might reveal the chemical composition and physical conditions within these mysterious cosmic objects. What he discovers defies every expectation about how celestial bodies should behave within the gravitational architecture of our galaxy. Slipher's spectroscopic technique requires extraordinary patience and precision. Each spiral nebula emits such faint light that obtaining usable spectra demands exposure, times measured in hours or even days, during which the telescope must track Earth's rotation with mechanical perfection to prevent star images from smearing across the photographic plate. The slightest vibration, atmospheric disturbance, or tracking error will blur the delicate spectral lines beyond useful resolution, making successful spectroscopy dependent on exceptional observing conditions and flawless instrumental performance. The spectrograph itself represents cutting-edge technology for its era, employing a carefully designed prism system to disperse incoming light into its component wavelengths. This dispersed light falls onto photographic emulsions sensitive to different portions of the electromagnetic spectrum, creating permanent records of stellar and nebula spectra that can be measured and analyzed long after the original observations. The technique allows astronomers to study the physical properties of distant objects through the characteristic wavelengths at which different chemical elements absorb or emit light. When Slipher examines his first successful spiral nebula spectrum, obtained from the Andromeda Nebula after weeks of painstaking observation, he notices immediately that something appears fundamentally wrong with the wavelength measurements. The characteristic absorption lines that should appear at specific wavelengths corresponding to hydrogen, calcium, and other common stellar elements seem systematically shifted toward longer, redder wavelengths than their laboratory standards predict. This redshift affects all spectral lines uniformly, suggesting some systematic effect rather than measurement error or instrumental malfunction. The magnitude of this wavelength shift proves far larger than anything previously observed in stellar spectra. Normal stellar motions within our galaxy, orbital velocities around the galactic center, random stellar movements through space, or binary star orbital motion typically produce wavelength shifts measurable in fractions of an angstrom unit. Yet the Andromeda Nebula's spectrum shows shifts of several angstroms, corresponding to velocities of approach or recession far exceeding any known stellar phenomenon. More puzzling still, the direction of this velocity proves to be approaching Earth rather than receding. According to the Doppler effect that governs wavelength shifts for moving sources, objects approaching an observer show spectral lines shifted towards shorter, bluer wavelengths, while receding objects display redshifted spectra with lines moved toward longer wavelengths. Andromeda's spectrum shows blue shift, indicating that this enormous spiral structure rushes toward our solar system at approximately 300 kilometers per second, a velocity that seems impossibly large for any object gravitationally bound within our galaxy. Such enormous approach velocity creates profound theoretical difficulties for understanding spiral nebula nature. If Andromeda truly represents a gas cloud or stellar association within our galaxy, then its 300 km per second approach velocity far exceeds the escape velocity from our galactic system. No gravitational mechanism can accelerate objects to such speeds within the confines of galactic architecture, suggesting that Andromeda either represents a completely different class of cosmic phenomenon or lies far beyond the boundaries of our local stellar neighborhood. Encouraged by this puzzling initial result, Slipher extends his spectroscopic survey to include additional spiral nebulae scattered across different regions of the sky. Each new spectrum requires weeks or months of careful observation, but the pattern that emerges proves even more mystifying than Andromeda's anomalous blue shift. Most spiral nebulae show spectral lines shifted toward longer, redder wavelengths, indicating recession velocities that range from hundreds to thousands of kilometers per second. These recession velocities exceed anything observed within our galaxy by factors of 10 or more. The fastest moving stars within the Milky Way, those with highly eccentric orbits that carry them far from the galactic plane, rarely achieve velocities exceeding 100 kilometers per second relative to the solar system. Yet spiral nebulae routinely display recession velocities of 500, 1,000, or even 1,500 kilometers per second, speeds that would carry them completely beyond the gravitational influence of our galaxy within relatively short astronomical timescales. The systematic nature of these high velocities proves particularly puzzling. If spiral nebulae were random objects within our galaxy, subject to normal gravitational dynamics, their velocities should show random distribution around the solar system's motion through space. Some should approach, others should recede, and the average velocity should approximate zero when measured across large samples. Instead, Slipher finds that the vast majority of spiral nebulae show recession rather than approach, suggesting some systematic effect that preferentially accelerates these objects away from our local cosmic neighborhood. The mathematical implications become even more troubling when Slipher calculates the kinetic energies associated with such enormous velocities. Objects with masses comparable to large stellar associations, moving at speeds of 1,000 kilometers per second, possess kinetic energies equivalent to the total gravitational binding energy of our entire galaxy. No known physical mechanism can provide the energy necessary to accelerate spiral nebulae to such speeds, particularly given the systematic preference for recession over approach that his observations reveal. Furthermore, if spiral nebulae truly move at such enormous speeds relative to our galaxy, then their distribution across the sky should change detectably over decades of observation. Objects moving at 1,000 kilometers per second at distances of a few thousand light-years should show measurable proper motion, angular displacement across the celestial sphere, within the time span of systematic astronomical observation. Yet spiral nebulae maintain fixed positions relative to background stars across decades of telescopic photography, suggesting either that they lie at much greater distances than their velocities would imply, or that their apparent motions result from some systematic effect rather than genuine spatial displacement. The spectroscopic measurements also reveal subtle details about spiral nebula composition that seem inconsistent with simple gaseous phenomena within our galaxy. The absorption lines detected in spiral nebula spectra sometimes show characteristics suggesting integrated starlight rather than emission from glowing gas clouds. These stellar signatures appear similar to those observed in globular star clusters, but with subtle differences that might indicate stellar populations with different chemical compositions or evolutionary histories than those found in our local galactic neighborhood. The breadth and complexity of absorption features in some spiral nebula spectra particularly intrigue Slipher. Simple gas clouds should display relatively few spectral lines corresponding to hydrogen and helium emission, with perhaps some heavier elements mixed into the glowing medium. Yet spiral nebulae sometimes show absorption spectra with dozens of subtle features suggesting the integrated light of many different stellar types: hot blue giants, cool red stars, and intermediate stellar masses, all contributing their characteristic spectral signatures to the combined light reaching terrestrial telescopes. These spectroscopic complexities suggest that spiral nebulae might represent stellar systems rather than gaseous phenomena, containing populations of stars with various masses, temperatures, and chemical compositions. If true, then the enormous velocities measured through Doppler spectroscopy would apply to entire stellar systems rather than individual gas clouds, implying energy scales and gravitational dynamics far beyond anything observed within our local galactic environment. Yet the systematic redshift pattern creates additional theoretical difficulties that extend beyond simple energy considerations. If spiral nebulae truly represent separate stellar systems moving at high velocities relative to our galaxy, then their redshift distribution should reflect the random motions expected from gravitational interactions between independent cosmic entities. Instead, the preferential recession observed by Slipher suggests some systematic effect that accelerates spiral nebulae away from our cosmic neighborhood, an effect that lacks any obvious physical explanation within the gravitational dynamics of the early 20th century. The observational challenges of extending spectroscopic measurements to fainter and more distant spiral nebulae push against the technological limitations of Slipher's era. Each spectrum requires increasingly long exposure times as spiral nebula brightness decreases, while atmospheric turbulence and instrumental limitations make it progressively more difficult to obtain reliable wavelength measurements for the faintest objects. The systematic survey of spiral nebula velocities awaits technological advances in telescope construction, photographic sensitivity, and spectroscopic precision. Despite these limitations, Slipher's velocity measurements provide the first quantitative evidence that spiral nebulae represent cosmic phenomena fundamentally different from any previously studied astronomical objects. Their enormous velocities and systematic recession patterns suggest that spiral nebulae exist in a realm of cosmic dynamics far removed from the gravitational architecture of our local stellar neighborhood. The universe reveals itself as containing objects and processes that exceed the explanatory power of contemporary astronomical theory. Throughout 1912 and the years immediately following, spiral nebulae continue their high-velocity motion through space, their light carrying Doppler-shifted spectral information across millions of years of travel to reach telescopes on Earth. Each photon preserves precise wavelength measurements that encode the velocity of its source, creating permanent records of cosmic motion that will not be fully understood for more than a decade. The universe broadcasts its dynamic nature to patient observers, revealing secrets about cosmic expansion and galactic recession that anticipate theoretical frameworks not yet developed by human science. The year settles into 1929, and Edwin Hubble sits at his desk at Mount Wilson Observatory, surrounded by photographic plates and measurement tables that contain the raw data for what will become one of the most profound discoveries in the history of science. Before him lie systematic measurements of galaxy distances derived from Cepheid variable stars, combined with Vesto-Slipher's velocity measurements obtained through spectroscopic analysis of galactic redshifts. When Hubble plots these two sets of measurements against each other, distance on one axis, recession velocity on the other, the pattern that emerges reveals a universe far stranger and more dynamic than anyone has previously imagined. The mathematical relationship appears almost impossibly simple for such a fundamental cosmic phenomenon. Galaxies at greater distances from Earth show proportionally greater recession velocities, with the ratio remaining essentially constant across the entire range of his measurements. A galaxy twice as far away recedes twice as fast. A galaxy 3 times more distant moves away at 3 times the velocity. This linear relationship holds with remarkable precision across distances, ranging from a few million light-years for nearby galaxies to tens of millions of light-years for the most distant objects he can measure reliably. The implications of this velocity-distance relationship challenge every assumption about cosmic architecture and gravitational dynamics. If galaxies truly recede from Earth with velocities proportional to their distances, then the universe itself must be expanding uniformly in all directions. Space itself stretches like an inflating balloon, carrying embedded galaxies away from each other at rates determined by their separation distances. This expansion affects not just the motion of galaxies through space, but the very geometry of space itself. Yet this interpretation requires abandoning fundamental assumptions about cosmic stability that have guided astronomical thinking since Newton's era. The universe has been assumed to represent a static, eternal structure, perhaps finite or infinite in extent, but unchanging in its overall architecture across cosmic time. Stars might be born and die, planets might form and evolve, but the large-scale structure of space itself was thought to remain constant throughout eternity. Hubble's observations suggest instead that the cosmos possesses a dynamic, evolving character that transforms its own geometric properties over time. The mathematical description of this cosmic expansion defies easy visualization through analogies with familiar physical systems. Unlike explosions that scatter matter through pre-existing space, cosmic expansion creates new space between existing objects rather than accelerating them through fixed spatial coordinates. Galaxies do not move through space at the velocities indicated by their redshifts. Instead, space itself expands, stretching the wavelengths of light traveling between galaxies and creating the observed Doppler shifts without requiring actual motion in the conventional sense. This distinction between expansion of space and motion through space resolves several puzzling aspects of galactic recession that have troubled astronomers since Slipher's first velocity measurements. The systematic preference for recession over approach, which seemed to violate basic principles of cosmic isotropy, results naturally from universal expansion that affects all directions equally. Earth occupies no special position within cosmic architecture. Observers on any galaxy would observe the same pattern of systematic recession in all directions, with recession velocities proportional to distance according to the same mathematical relationship. Furthermore, universal expansion explains why galactic recession velocities can exceed the escape velocity from our local gravitational neighborhood without violating energy conservation principles. Galaxies do not acquire kinetic energy by accelerating through space. Instead, the expansion of space itself creates the observed redshifts without requiring energy expenditure for acceleration. The universe expands not because some external force pushes galaxies apart, but because expansion represents the natural evolution of cosmic geometry itself. The rate of this cosmic expansion, as measured by the proportionality constant relating recession velocity to distance, provides the first quantitative measure of cosmic evolution timescales. Hubble calculates that galaxies separate from each other at approximately 500 kilometers per second per megaparsec of distance, meaning that galaxies separated by 3.26 million light-years recede from each other at 500 kilometers per second. This expansion rate implies that any given pair of galaxies doubles their separation distance approximately every 2 billion years. Extrapolating this expansion backward in time leads to profound conclusions about cosmic history. If galaxies currently separate at rates proportional to their distances, then they must have been closer together in the past, with separation distances shrinking towards zero as one traces cosmic evolution further backward. This mathematical extrapolation suggests that the entire observable universe emerged from an extremely compact initial state approximately 2 billion years ago, a cosmic genesis event that initiated the expansion process still continuing today. Yet this time, scale creates immediate conflicts with independent estimates of cosmic age derived from stellar evolution theory and geological dating. Stars in globular clusters appear to be burning steadily for periods much longer than 2 billion years, while geological evidence suggests that Earth itself has existed for several billion years with relatively stable surface conditions. The expansion timescale derived from Hubble's measurements seems too short to accommodate the evolutionary history required by astronomy and geology. This temporal contradiction highlights systematic errors in the distance, measurements underlying Hubble's expansion rate calculation, the period luminosity relationship for Cepheid variables, which provides the foundation for extragalactic distance measurement, depends on calibration observations of Cepheids within our own galaxy. But these calibration distances themselves contain significant uncertainties due to interstellar dust extinction, stellar population differences, and the technical limitations of 1920s astrometric measurements. Interstellar dust presents a particularly subtle source of systematic error in distance determination. Fine particles scattered throughout galactic space absorb and scatter starlight, making distant objects appear fainter than they would in perfectly transparent space. This dimming effect causes distance estimates to be systematically too large, since astronomers interpret the reduced brightness as evidence for greater distance rather than recognizing the effects of intervening dust. The systematic overestimate of distances leads to correspondingly large values for the cosmic expansion rate and correspondingly short estimates for cosmic age. The identification and measurement of Cepheid variables in distant galaxies also presents significant observational challenges that introduce additional uncertainties into distance determinations. Even the most powerful telescopes available to Hubble can barely resolve individual stars in nearby galaxies, making it difficult to distinguish genuine Cepheid variables from other types of variable stars or from photometric artifacts caused by atmospheric turbulence and instrumental limitations. Furthermore, the assumption that Cepheid variables in distant galaxies follow the same period-luminosity relationship as those in our local galactic neighborhood may not hold across different stellar populations and galactic environments. Stars formed in galaxies with different chemical compositions, star formation histories, or gravitational architectures might exhibit different pulsation properties that could systematically bias distance measurements derived from period luminosity calibrations based on local galactic standards. Despite these systematic uncertainties, Hubble's discovery of the velocity-distance relationship provides the first quantitative evidence for cosmic evolution on the largest observable scales. The universe reveals itself as a dynamic, evolving entity rather than a static, eternal structure, with its current configuration representing just one phase in an ongoing process of geometric transformation that began in the remote cosmic past and continues into the indefinite future. The philosophical implications of cosmic expansion prove as profound as the scientific ones. If the universe possesses a finite age determined by extrapolating current expansion rates backward to an initial singularity, then cosmic evolution resembles biological development more than mechanical clockwork. The universe emerges, evolves, and potentially approaches some ultimate fate determined by the physical laws governing cosmic dynamics across vast temporal scales. Yet the ultimate fate of cosmic expansion remains entirely uncertain within the theoretical frameworks available to Hubble's era. Will expansion continue indefinitely, carrying galaxies ever farther apart until they disappear beyond each other's observational horizons? Or will gravitational forces eventually reverse the expansion, causing the universe to contract back toward another singularity in the remote future? The answer depends on the total mass and energy content of the universe, quantities that remain unmeasured and perhaps unmeasurable using 1920s astronomical techniques. The discovery of cosmic expansion also raises fundamental questions about the nature of space and time themselves. If space expands, carrying embedded matter along with it, then space possesses physical properties more complex than the simple three-dimensional container envisioned by classical physics. The geometry of space itself becomes subject to physical laws and evolutionary processes, suggesting deep connections between gravitational theory, cosmic architecture, and the mathematical foundations of physics. Throughout 1929 and beyond, galaxies continue their systematic recession from our cosmic neighborhood, their light carrying redshift information across millions of years of expanding space to reach telescopes on Earth. Each photon encodes precise measurements of cosmic expansion that will gradually refine humanity's understanding of universal dynamics and cosmic evolution. The universe reveals its most fundamental characteristic: ongoing expansion that transforms cosmic architecture across vast scales of time and space. To observers equipped with sufficient observational precision and conceptual sophistication to recognize the significance of galactic recession velocities. Meanwhile, the cosmic expansion continues its patient work, stretching space itself and carrying galaxies away from each other at rates that will not be accurately measured for several more decades. The universe expands, vast and inexorable, following mathematical laws that govern cosmic evolution across temporal and spatial scales that challenge human comprehension, yet yield their secrets to careful observation and mathematical analysis. The year moves through 1933, and Fritz Zwicky peers through the eyepiece of the 18-inch Schmidt telescope at Mount Wilson Observatory, systematically photographing the Coma cluster of galaxies. This enormous galactic aggregation contains over 1,000 individual galaxies clustered within a relatively small volume of space, their combined gravitational forces binding them into the largest coherent structures yet discovered in the cosmic architecture. What Zwicky seeks to measure, the total mass of this galactic congregation, will reveal the first evidence for a cosmic mystery that will haunt astronomy for the remainder of the 20th century and beyond. Zwicky's approach combines careful observational technique with straightforward Newtonian mechanics. By measuring the velocities at which individual galaxies move within the cluster, and applying the virial theorem that relates kinetic energy to gravitational potential energy in bound systems, he can calculate the total mass necessary to hold the cluster together against the dispersive effects of galactic orbital motion. The mathematics follows directly from principles established by Newton 3 centuries earlier, requiring only precise measurements of galactic positions, distances, and velocities to yield reliable mass estimates. The velocity measurements themselves demand extraordinary observational precision. Each galaxy within the Coma cluster emits extremely faint light that must be analyzed spectroscopically to detect the small Doppler shifts that reveal orbital velocities. These spectroscopic observations require exposure times measured in hours, during which atmospheric turbulence, instrumental flexure, and tracking errors all contribute noise to the delicate wavelength measurements necessary for reliable velocity determination. When Zwicky completes his systematic survey of galactic velocities within the Coma cluster, the results defy every expectation based on the visible stellar content of the constituent galaxies. The orbital velocities prove far too large for the cluster to remain gravitationally bound if its mass consisted only of the stars visible through telescopic observation. Simple calculations based on stellar populations suggest that the cluster should have dispersed billions of years ago, its constituent galaxies scattered across cosmic space by their excessive orbital energies, yet the Coma cluster obviously exists as a stable, gravitationally bound system. The galaxies show no signs of escaping from their mutual gravitational embrace, and the cluster maintains its compact configuration across the millions of years required for light to travel from its distant location to terrestrial telescopes. This observational fact, the cluster's continued existence, demands that its total mass significantly exceeds the visible stellar content by factors that seem almost impossible to reconcile with conventional understanding of galactic composition. Zwicky calculates that the cluster requires approximately 400 times more mass than can be accounted for by visible stars to provide sufficient gravitational binding for the observed orbital velocities. This missing mass must somehow remain completely invisible to optical telescopes while contributing its full gravitational influence to cluster dynamics. The implications challenge fundamental assumptions about the relationship between visible matter and gravitational mass that have guided astronomical thinking since Newton's era. The nature of this invisible mass presents profound theoretical puzzles that extend far beyond simple observational uncertainties. If the missing mass consists of ordinary stellar material, perhaps very faint stars too dim for telescopic detection, then stellar formation processes within cluster galaxies must differ dramatically from those observed in our local galactic neighborhood. The vast majority of stellar mass would need to reside in objects far too faint to contribute detectably to galactic luminosity, yet massive enough to dominate gravitational dynamics. Alternatively, the missing mass might consist of completely different types of matter that interact gravitationally but emit no detectable electromagnetic radiation. Such dark matter would represent a previously unknown component of cosmic architecture, contributing the majority of universal mass while remaining completely invisible to optical, radio, and photographic observation techniques. This possibility suggests that the visible universe, stars, galaxies, and nebulae revealed through telescopic study, represents only a small fraction of total cosmic matter content. The systematic nature of Zwicky's mass discrepancy, found consistently across multiple galaxy clusters, argues against simple measurement errors or observational artifacts. Each cluster studied shows similar patterns of excessive orbital velocities that require dark mass components far exceeding visible stellar populations. The missing mass problem appears to be a fundamental characteristic of large-scale cosmic structure rather than an anomaly specific to particular galactic systems. Yet the detection and study of dark matter presents seemingly insurmountable observational challenges using available astronomical techniques. By definition, dark matter emits no light across any portion of the electromagnetic spectrum, making it completely invisible to optical telescopes, radio receivers, photographic plates, and spectroscopic analysis. Its presence can be inferred only through gravitational effects on visible matter, orbital velocities, gravitational lensing, or other dynamical signatures that reveal the presence of unseen mass. The theoretical implications of dark matter extend beyond astronomy into fundamental physics. If dark matter consists of previously unknown types of particles that interact gravitationally but not electromagnetically, then particle physics must accommodate entire classes of matter not yet discovered through terrestrial experiments. The universe might contain vast quantities of exotic particles that pass through ordinary matter without detectable interaction, except through their gravitational influence on cosmic structure. This possibility suggests deep connections between cosmology and particle physics that were previously unsuspected. The study of galaxy cluster dynamics might reveal fundamental properties of matter and energy that cannot be detected through laboratory experiments, making astronomical observation an essential tool for discovering the basic constituents of physical reality. The cosmic laboratory provides access to energy scales, particle densities, and physical conditions impossible to reproduce through terrestrial experimentation. The energy scales involved in galaxy cluster dynamics also raise questions about the formation and evolution of large-scale cosmic structure. If dark matter dominates the mass content of galaxy clusters, then the gravitational forces that assembled these enormous structures must have operated primarily through dark matter interactions rather than the stellar and gaseous processes visible through telescopic observation. The visible components of galaxies, stars, gas clouds, and dust might represent minor additions to underlying dark matter frameworks established through purely gravitational dynamics. This scenario implies that cosmic structure formation follows a more complex evolutionary pathway than previously imagined. Dark matter might have begun collapsing into hierarchical structures long before ordinary matter could cool sufficiently to form stars and galaxies. The visible universe would then represent a secondary process, with stars and gas settling into gravitational wells already established by dark matter condensation. Yet the specific properties required for dark matter to play such a dominant role in cosmic evolution remain completely unknown. Dark matter particles must be stable enough to persist across billions of years of cosmic evolution, yet weakly interacting enough to avoid detection through electromagnetic observation. They must be sufficiently numerous to provide the observed gravitational effects, yet maintain particle properties that allow them to form bound structures without radiating energy through electromagnetic processes. The search for direct evidence of dark matter requires developing entirely new observational techniques that can detect gravitational effects without relying on electromagnetic radiation. Gravitational lensing, the bending of light from distant objects by intervening mass concentrations, might provide one approach for mapping dark matter distributions throughout cosmic space. The subtle distortions of background galaxy images could reveal the presence of dark matter structures invisible to conventional telescopic observation. Alternatively, the motion of gas clouds within galaxy clusters might trace the gravitational influence of dark matter through hydrodynamic effects that can be observed through radio astronomy and X-ray detection. Hot gas falling into dark matter gravitational wells should emit characteristic radiation signatures that reveal both the distribution and total mass of invisible matter components. Throughout 1933 and the decades that follow, dark matter continues its silent gravitational influence on cosmic structure, binding galaxy clusters together while remaining completely invisible to all forms of electromagnetic observation. Its presence shapes the evolution of cosmic architecture on the largest observable scales, yet its fundamental nature remains as mysterious as any phenomenon in the history of science. The universe reveals itself as far stranger and more complex than visible matter alone would suggest. The majority of cosmic mass exists in forms completely undetectable through conventional astronomical observation, creating gravitational scaffolding that supports the visible structures revealed through telescopic study. Dark matter governs cosmic evolution through purely gravitational interactions, shaping the universe through invisible influences that exceed the combined gravitational effects of all visible stars and galaxies. The year moves through 1931, and Carl Jansky adjusts the rotating antenna array he has constructed in a field near Holmdel, New Jersey, for Bell Telephone Laboratories. His assignment involves investigating sources of radio interference that might disrupt long-distance telephone communications, a mundane engineering problem that will accidentally open an entirely new window for observing the cosmos. As his antenna system slowly rotates through its daily cycle, systematically sampling radio noise from all directions across the sky, Jansky notices a persistent signal that appears to follow celestial coordinates rather than terrestrial sources of interference. This mysterious radio signal peaks in intensity approximately 4 minutes earlier each day, matching the sidereal rhythm that governs stellar motion across Earth's sky. Unlike terrestrial radio sources that maintain fixed relationships to solar time, Jansky's signal follows the rotation of celestial coordinates, suggesting an origin somewhere among the stars rather than from lightning, electrical equipment, or other earthbound phenomena. The signal's celestial timing provides the first evidence that cosmic objects emit detectable radio waves across vast distances of space. More intriguingly, the radio emission appears strongest when Jansky's antenna points toward the constellation Sagittarius, particularly toward the dense star clouds that mark the direction of our galaxy's center. This directional correspondence suggests that radio waves originate from the concentrated stellar populations within the Milky Way's central regions, where billions of stars cluster within relatively small volumes of space. Yet no theoretical framework exists for understanding how stellar objects might generate radio emissions detectable across galactic distances. The discovery challenges fundamental assumptions about electromagnetic radiation from cosmic sources. Stars emit energy primarily as visible light and infrared radiation, with surface temperatures determining the wavelength distribution of their electromagnetic output according to well-established thermal physics. Radio waves, with their much longer wavelengths and lower photon energies, should represent only negligible fractions of total stellar energy output, far too weak for detection using terrestrial radio receivers across galactic distances. Furthermore, the intensity and characteristics of Jansky's radio signals seem inconsistent with thermal emission from stellar surfaces. The radio brightness temperature, the temperature that a perfect blackbody radiator would need to produce the observed radio intensity, exceeds stellar surface temperatures by enormous factors, suggesting non-thermal emission mechanisms that remain completely unknown to 1930s physics. The radio signals imply energy conversion processes far more efficient than simple thermal radiation for generating electromagnetic emission at radio wavelengths. The systematic nature of the radio emission, with its precise correlation to galactic coordinates and its concentration toward the galactic center, argues against simple instrumental artifacts or terrestrial interference sources. Jansky's antenna system rotates through a complete cycle every 24 hours, allowing systematic comparison of radio intensity from all sky directions. The consistency with which maximum signal strength corresponds to galactic center culmination provides strong evidence for genuine cosmic radio sources. Yet the interpretation of these radio signals remains deeply puzzling within the scientific frameworks available during Jansky's era. Radio astronomy does not yet exist as a recognized scientific discipline, and theoretical physics lacks conceptual tools for understanding non-thermal electromagnetic emission from cosmic sources. The radio emissions represent phenomena completely outside the experience of optical astronomy, requiring entirely new theoretical approaches and observational techniques. The technical challenges of extending radio astronomical observations beyond Jansky's initial discovery prove formidable using 1930s technology. Radio receivers require enormous collecting areas to achieve sufficient sensitivity for detecting faint cosmic signals, while directional antennas must maintain precise pointing accuracy to map radio source positions against stellar coordinates. Both requirements push against the technical capabilities of early radio engineering. More fundamentally, radio waves suffer significant interference from terrestrial sources that complicate the detection and study of weak cosmic signals. Lightning produces intense radio noise across wide frequency ranges, while electrical equipment generates interference that can mask genuine astronomical emissions. Urban environments create particularly severe radio pollution that makes cosmic radio astronomy extremely challenging, except from specially selected remote locations. The development of radio astronomy also requires solving complex theoretical problems about radio wave propagation through Earth's atmosphere and interplanetary space. Different radio frequencies penetrate Earth's ionosphere with varying efficiency, while interstellar space contains free electrons that can scatter or absorb radio waves through mechanisms not yet understood. The relationship between radio emission at Earth and radio generation at distant cosmic sources remains entirely theoretical throughout the 1930s. Despite these technical and theoretical challenges, Jansky's discovery provides the first evidence that the universe broadcasts across electromagnetic wavelengths far beyond the narrow range accessible to optical telescopes. Cosmic objects emit radio waves that carry information about physical processes invisible to conventional astronomical observation, opening possibilities for studying entirely different aspects of stellar and galactic physics through radio detection and analysis. The energy mechanisms responsible for galactic radio emission particularly intrigue theoretical physicists attempting to understand Jansky's observations. If radio waves originate from the galactic center regions, where stellar densities reach maximum values, then radio emission might result from interactions between stellar magnetic fields, charged particle acceleration, or other high-energy processes occurring within dense stellar environments. Such mechanisms would operate according to physical principles completely different from the thermal radiation that governs visible stellar emission. Alternatively, radio emission might originate from interstellar matter, gas and dust clouds scattered throughout galactic space, rather than from stellar objects themselves. Ionized hydrogen pervading interstellar regions might emit radio waves through atomic transitions not visible at optical wavelengths, while magnetic fields threading through galactic space might accelerate charged particles to energies sufficient for radio emission through synchrotron radiation processes. These theoretical possibilities suggest that radio astronomy might reveal aspects of cosmic architecture invisible to optical observation, interstellar space, which appears largely empty through telescopic study except for occasional bright nebulae, might contain vast quantities of matter detectable only through radio emission. The structure and dynamics of galactic magnetic fields, completely inaccessible through optical techniques, might be mapped through radio polarization measurements and synchrotron emission analysis. The systematic exploration of cosmic radio sources awaits technological developments that will not occur for another decade. Radio telescope construction requires engineering expertise that combines radio frequency technology with astronomical precision, creating instruments capable of detecting microwave-level signals from cosmic distances while maintaining pointing accuracies measured in arc-minutes or arc-seconds. The marriage of radio engineering and astronomical observation creates entirely new technical challenges, yet the potential scientific rewards justify these technical investments. Radio astronomy promises access to cosmic phenomena completely invisible to optical telescopes, including the study of interstellar matter, galactic magnetic fields, high-energy particle acceleration, and emission mechanisms that operate through non-thermal physical processes. The radio universe might contain objects and phenomena that emit little or no visible light, yet dominate cosmic evolution through processes detectable only at radio wavelengths. Throughout the 1930s and beyond, cosmic radio sources continue broadcasting their electromagnetic signals across the galaxy, their radio waves traveling at the speed of light through interstellar space to reach Earth's ionosphere. Each radio photon carries information about emission mechanisms, magnetic field structures, and high-energy processes occurring within environments far too extreme for terrestrial replication. The universe reveals its radio voice to listeners equipped with sufficient technical sophistication to distinguish cosmic signals from terrestrial interference. The discovery that galaxies emit radio waves represents humanity's first detection of non-optical cosmic phenomena, opening research directions that will transform astronomical understanding throughout the remainder of the 20th century. Radio astronomy reveals the universe as an active, dynamic environment where magnetic fields accelerate particles to enormous energies and matter exists in physical states impossible to study through visible light observation alone. The year drifts through 1963, and Martin Schmidt peers at photographic spectra obtained through the 200-inch Hale telescope at Palomar Observatory. Attempting to understand the nature of a peculiar stellar object designated 3C273. This object appears perfectly star-like through optical telescopes, a single point of light indistinguishable from ordinary stars in our galactic neighborhood, yet emits radio waves with intensities far exceeding any known stellar radio source. The combination of stellar optical appearance with anomalous radio properties has puzzled astronomers since radio telescopes first detected these quasi-stellar radio sources scattered across the sky. Schmidt's spectroscopic analysis reveals characteristics that challenge every assumption about stellar physics and cosmic energy generation. The spectrum of 3C273 shows broad emission lines that initially resist identification with any known atomic or molecular transitions. The wavelengths seem too long for hydrogen, helium, or other common stellar elements. Yet the line profiles and intensities suggest emission from highly ionized gases at enormous temperatures and densities. For weeks, Schmidt struggles to match the observed spectral features with laboratory standards of known elements. The breakthrough comes when Schmidt realizes that the mysterious emission lines represent familiar hydrogen transitions shifted to much longer wavelengths by the Doppler effect. But the required redshift, approximately 16% increase in wavelength, corresponds to recession velocities of nearly 50,000 kilometers per second, far exceeding any velocity previously measured for stellar objects within our galaxy. Such enormous velocities would carry any stellar object completely beyond the gravitational influence of the Milky Way within relatively short astronomical timescales. More troubling still, if 3C273 truly recedes at 50,000 kilometers per second, according to Hubble's velocity-distance relationship for cosmic expansion, then it lies at distances of approximately 2 billion light-years from Earth. At such cosmic distances, 3C273 must emit total energy equivalent to hundreds of billions of suns burning simultaneously to appear as bright as it does through terrestrial telescopes. This energy requirement exceeds the total luminosity of entire galaxies, yet emerges from a region small enough to appear stellar through the most powerful optical telescopes available. The implications defy comprehension within existing frameworks of stellar physics and energy generation. No known mechanism can sustain energy outputs comparable to entire galaxies, while confining the emission region to volumes small enough to appear point-like through telescopic observation. Nuclear fusion, which powers normal stellar luminosity, cannot provide sufficient energy density for quasi-stellar energy requirements, even if matter conversion proceeded with perfect efficiency according to Einstein's mass-energy relationship. Schmidt's discovery opens systematic searches for additional quasi-stellar objects. revealing that these enigmatic sources scatter throughout the observable universe at distances ranging from hundreds of millions to billions of light-years from Earth. Each new quasi-stellar object, quickly abbreviated to quasar by the astronomical community, displays similar characteristics: stellar optical appearance combined with enormous luminosity, broad emission lines indicating highly ionized gases, and recession velocities that place them among the most distant objects ever detected through astronomical observation. The energy problem becomes even more acute when astronomers discover that many quasars show rapid brightness variations over timescales of days, weeks, or months. These variability patterns indicate that quasar emission regions cannot exceed light travel distances corresponding to the observed variation timescales. An object that brightens significantly within 1 week must have physical dimensions smaller than 1 light week. Since no physical process can coordinate brightness changes across larger regions faster than light can travel between different parts of the emission zone, this light travel constraint forces quasar emission into volumes smaller than our solar system. Yet these microscopic regions, by cosmic standards, must generate energy outputs exceeding entire galactic populations of hundreds of billions of stars. The energy density requirements approach theoretical limits imposed by fundamental physics, suggesting emission mechanisms far beyond any previously contemplated astronomical phenomenon. The spectroscopic properties of quasars reveal additional puzzles that challenge understanding of cosmic evolution and galaxy formation. The broad emission lines originate from gas clouds moving at velocities of thousands of kilometers per second within the quasar environment, indicating gravitational fields or explosive phenomena far more energetic than any process observed within normal stellar systems. The gas temperatures implied by ionization levels reach millions of degrees, creating physical conditions more extreme than stellar interiors. Furthermore, the heavy element abundances revealed through quasar spectroscopy suggest that these distant objects contain processed stellar material, carbon, nitrogen, oxygen, and iron that must have been synthesized within stellar cores and dispersed through supernova explosions. Yet quasars exist at such enormous distances that their light began traveling toward Earth when the universe was only a fraction of its current age. The presence of heavy elements in such early cosmic epochs requires stellar formation and evolution to have proceeded much more rapidly than current theories predict. The spatial distribution of quasars across cosmic distances provides additional clues about cosmic evolution that seem to conflict with conventional understanding of universal homogeneity. Quasars appear most numerous at intermediate redshifts corresponding to cosmic epochs several billion years in the past, with relatively few examples found either nearby or at the most extreme distances accessible through telescopic observation. This distribution suggests that quasar phenomena flourish during specific periods of cosmic history rather than maintaining steady occurrence rates across all epochs. The apparent absence of nearby quasars particularly puzzles astronomers attempting to understand quasar physics through detailed observation. If quasar phenomena represent ongoing cosmic processes, then some examples should exist within our local cosmic neighborhood where their emission mechanisms could be studied with high spatial and temporal resolution. Yet systematic searches fail to identify any nearby objects with quasar characteristics, suggesting that quasar activity ceased in our cosmic vicinity billions of years ago. This temporal evolution implies connections between quasar phenomena and cosmic structure formation that remain completely mysterious. Perhaps quasar activity requires specific environmental conditions, dense matter concentrations, primordial gas compositions, or gravitational architectures that existed during earlier cosmic epochs but have since evolved into different configurations. The relationship between quasar evolution and galaxy formation awaits theoretical frameworks not yet developed. The energy source powering quasar emission represents perhaps the most fundamental unsolved problem in all of astronomy. Conventional stellar processes, nuclear fusion. Gravitational contraction, magnetic field interactions, cannot account for the enormous energy outputs observed from such compact emission regions. Entirely new physical mechanisms must operate within quasar environments, possibly involving gravitational energy release through matter accretion onto extremely compact objects or energy conversion processes that approach theoretical efficiency limits. The discovery of quasars forces astronomy to confront energy scales and physical processes that extend far beyond terrestrial experience or laboratory replication. These cosmic beacons shine across billions of light years with luminosities that dwarf entire galactic populations, yet confine their emission to regions smaller than planetary orbits. They represent the universe operating at maximum energy density, revealing physical processes that push against fundamental limits imposed by relativity, quantum mechanics, and gravitational theory. Throughout 1963 and beyond, quasars continue broadcasting their enormous energy outputs across cosmic space, their light traveling billions of years through expanding universe to reach telescopes on Earth. Each photon carries information about emission mechanisms, gravitational environments, and physical processes that operate under conditions impossible to reproduce through any terrestrial experimentation. The universe reveals its most energetic phenomena to observers equipped with sufficient observational sophistication to recognize stellar appearances that mask galactic-scale energy generation. Meanwhile, the systematic study of quasar properties awaits technological advances in spectroscopic precision, radio interferometry, and theoretical physics that will gradually reveal the gravitational and electromagnetic processes responsible for such extraordinary cosmic energy sources. The universe operates its most powerful engines in regions smaller than solar systems, converting matter into energy with efficiencies that approach theoretical perfection through mechanisms not yet understood by human science. The year settles into 1964, and Lin Chiachiao sits at his desk at the Massachusetts Institute of Technology, working through mathematical equations that describe the rotation of spiral galaxies and the persistence of their elegant arm patterns. His calculations address a fundamental puzzle that has troubled astronomers since the first spiral nebulae were discovered through telescopic observation. If spiral galaxies rotate as solid bodies, their spiral patterns should wind up and disappear within a few 100 million years. Yet spiral structures persist throughout cosmic time in galaxies billions of years old. The mathematical framework for this winding problem follows directly from observational measurements of galactic rotation. Radio astronomy has revealed that spiral galaxies rotate differentially. Their inner regions complete orbital cycles faster than their outer edges, creating shear forces that should wrap spiral patterns tighter and tighter with each passing rotation. Simple calculations suggest that any spiral pattern should become completely wound up within 10 to 20 galactic rotation periods. Yet spiral galaxies maintain crisp, well-defined arm structures across cosmic timescales spanning hundreds of rotation cycles. Lin's density wave theory proposes an elegant solution to this temporal paradox. Rather than treating spiral arms as material structures that rotate with galactic matter, his mathematical analysis describes them as pressure waves that propagate through the galactic disk at velocities different from stellar orbital speeds. These density waves create regions of enhanced stellar formation and gas compression that appear bright against the galactic background, making spiral patterns visible without requiring the arms themselves to consist of persistent material structures. The mathematics of density wave propagation through rotating galactic disks proves surprisingly complex, involving fluid dynamics, gravitational theory, and wave mechanics applied to systems containing billions of stellar masses distributed across volumes tens of thousands of light-years in diameter. The wave equations must account for gravitational self-attraction, rotational shear forces, gas pressure gradients, and stellar velocity dispersions that all contribute to wave propagation characteristics through galactic environments. According to Lind's calculations, spiral density waves travel around galactic disks at speeds slightly different from stellar orbital velocities, creating patterns that persist while individual stars and gas clouds move through them. Stars spend portions of their orbits within spiral arms, where enhanced gravitational fields and gas densities trigger increased stellar formation rates, then continue their orbital motion into interarm regions where stellar formation proceeds at lower background rates. The spiral patterns remain visible because they continuously collect new stellar populations rather than because the same stars always remain within arm structures. This wave propagation model explains several observational characteristics of spiral galaxies that had previously resisted theoretical understanding. Young, bright stars concentrate preferentially within spiral arms because recent stellar formation occurs primarily within the compressed gas regions created by passing density waves. Older stellar populations show much weaker spiral patterns because they formed throughout galactic disks before density wave compression organized them into spiral configurations. The model also predicts specific relationships between spiral arm pitch angles, galactic rotation rates, and stellar velocity dispersions that can be tested through systematic observational programs. Galaxies with different rotation characteristics should display spiral patterns with correspondingly different geometric properties, while variations in stellar population ages should correlate with spiral arm contrast and persistence across different galactic types. Yet the physical mechanisms responsible for generating and maintaining spiral density waves remain completely mysterious within Lind's theoretical framework. Density waves require energy sources to compensate for dissipative processes that would otherwise damp wave amplitudes over galactic dynamical timescales. Some form of wave-driving mechanism must continuously inject energy into spiral patterns to maintain their observed amplitudes across billions of years of galactic evolution. Possible wave-driving mechanisms include gravitational interactions with companion galaxies, central mass concentrations that create non-axisymmetric gravitational potentials, or instabilities within galactic disks themselves that spontaneously generate spiral perturbations. Each possibility requires specific galactic environmental conditions that may or may not apply to the full range of spiral galaxies observed throughout the universe. The companion galaxy hypothesis suggests that gravitational tides from nearby galactic neighbors create periodic disturbances that drive spiral wave patterns within galactic disks. These tidal interactions would vary in strength depending on companion masses, separation distances, and orbital characteristics, potentially explaining the diversity of spiral patterns observed across different galactic environments. Yet many spiral galaxies appear isolated from significant companions, suggesting that tidal driving cannot provide a universal mechanism for spiral wave generation. Central mass concentrations present another potential wave-driving mechanism, particularly if galactic nuclei contain compact objects with masses comparable to millions of stellar masses. Non-circular gravitational potentials created by central mass distributions could generate spiral perturbations that propagate outward through galactic disks, maintaining spiral patterns through continuous energy injection from central regions. The recent discovery of quasars and other energetic galactic nuclei suggests that galactic centers might indeed contain exotic objects capable of influencing large-scale galactic structure. Alternatively, spiral patterns might arise from instabilities intrinsic to rotating galactic disks rather than from external driving mechanisms. Gravitational instabilities, magnetorotational turbulence, or stellar feedback processes might spontaneously generate spiral perturbations that grow and persist through nonlinear dynamical processes. These self-organizing mechanisms would require no external energy sources, instead drawing power from gravitational potential energy or rotational kinetic energy stored within galactic disks themselves. The observational testing of spiral density wave theory requires technological advances in radio astronomy, infrared detection, and stellar population analysis that push against the capabilities of 1960s astronomical instrumentation. Mapping gas velocities throughout spiral galaxies demands radio-telescopic resolution sufficient to trace orbital motion within individual spiral arms, while distinguishing stellar age populations requires photometric precision across multiple wavelength bands to separate young blue stars from older red populations. More fundamentally, density wave theory makes specific predictions about gas flow patterns within spiral arms that can be tested through high-resolution radio observations of hydrogen emission. Gas should flow into spiral arms from leading edges, experience compression and shock heating within arm regions, then flow out through trailing edges with modified velocities and densities. These flow patterns should create detectable signatures in radio spectroscopy that can confirm or refute the basic assumptions underlying wave propagation models. The theory also predicts systematic relationships between stellar formation rates and spiral arm passage that should be observable through photometric studies of resolved stellar populations. Young stellar associations should correlate strongly with current spiral arm positions, while older stellar groups should show progressively weaker correlations reflecting their formation during earlier spiral arm configurations. Long-term photometric monitoring might even detect stellar formation rate variations as gas clouds orbit through successive spiral arm passages. Yet the application of density wave theory to specific galactic systems reveals complications that suggest the mathematical framework remains incomplete. Real spiral galaxies display asymmetries, branching patterns, and time-variable characteristics that differ significantly from the symmetric. Steady-state wave solutions derived through Lind's mathematical analysis, galaxy interactions, stellar feedback processes, and magnetic field effects all contribute complexities not included in simplified wave propagation models. The diversity of spiral patterns observed across different galactic types also challenges universal applicability of density wave mechanisms. Some galaxies display grand design spiral patterns with two symmetric arms extending across entire galactic disks, while others show multiple arm fragments, ring structures, or completely irregular stellar distributions. This morphological diversity suggests that multiple physical processes contribute to spiral pattern formation, with density waves representing just one among several competing mechanisms. Furthermore, the temporal evolution of spiral patterns remains largely theoretical due to the impossibility of observing galactic changes over human timescales. Density wave theory makes specific predictions about how spiral patterns should evolve over millions of years as wave amplitudes grow or decay in response to changing galactic conditions. But these predictions cannot be tested through direct observation of galactic evolution. Computer simulations offer potential alternatives to direct observation for testing theoretical predictions about spiral pattern evolution, but computational capabilities in the 1960s remain far too limited for realistic modeling of galactic dynamics. Simulating the gravitational interactions and fluid dynamics of billions of stellar and gas particles over millions of years requires computational resources that will not become available for several more decades. The mathematical complexity of density wave theory also limits its practical application to real galactic systems with irregular mass distributions, asymmetric rotation curves, and complex stellar population histories. The analytical solutions derived by Lind apply primarily to idealized galaxies with symmetric mass distributions and simple rotation patterns, while real galaxies display gravitational potentials far too complex for exact mathematical treatment. Despite these limitations, density wave theory provides the first physically plausible explanation for spiral pattern persistence across galactic evolution timescales. The mathematical framework offers testable predictions about gas dynamics, stellar formation patterns, and spiral arm characteristics that can guide observational programs designed to understand galactic structure and evolution. The theory transforms spiral arms from mysterious persistent features into manifestations of wave physics operating within gravitational environments. Throughout the 1960s and beyond, spiral galaxies continue their slow rotation against the cosmic background, their spiral patterns maintained through wave propagation mechanisms that remain only partially understood. Each galactic rotation cycle carries matter through spiral arms, while preserving arm patterns through density wave propagation, creating the persistent spiral structures that have puzzled astronomers since telescopic discovery of spiral nebulae. The mathematical description of these wave processes awaits computational advances and observational techniques that will gradually reveal the complex interactions between gravitational dynamics, gas physics, and stellar formation that create and maintain spiral patterns across cosmic time. Spiral galaxies rotate, vast and patient, following mathematical laws that govern wave propagation through gravitational fields, while revealing their secrets only to observers equipped with sufficient theoretical and technological sophistication to recognize wave phenomena operating across galactic scales. The year moves through 1998, and two independent research teams led by Saul Perlmutter and Brian Schmidt prepare to announce discoveries that will fundamentally challenge humanity's understanding of cosmic evolution and the ultimate fate of the universe. Their systematic studies of distant supernovae, stellar explosions so powerful they briefly outshine entire galaxies, have revealed that cosmic expansion is not slowing down under gravitational attraction as all theoretical models predict, but instead accelerating at an ever-increasing rate driven by some unknown form of energy that opposes gravitational contraction. The supernova observations rely on a specific class of stellar explosions known as Type Ia supernovae, which occur when white dwarf stars accumulate matter from companion stars until they reach a critical mass threshold that triggers catastrophic nuclear burning. These explosions produce remarkably uniform peak brightnesses because they always involve the same critical mass of nuclear fuel burning under identical physical conditions, making them ideal standard candles for measuring cosmic distances across billions of light years. By combining supernova distance measurements with redshift observations that reveal recession velocities, astronomers can map the expansion history of the universe with unprecedented precision. If cosmic expansion has been slowing down over time due to gravitational attraction between galaxies, then distant supernovae, whose light reveals cosmic conditions billions of years ago, should appear brighter than nearby supernovae because the universe was expanding more slowly when their light began its journey toward Earth. Instead, the supernova observations reveal exactly the opposite pattern. Distant supernovae appear systematically fainter than theoretical predictions based on decelerating expansion models, indicating that cosmic expansion has been accelerating throughout the time period sampled by the supernova data. The universe expanded more slowly in the past than current expansion rates would suggest, meaning that cosmic expansion has been speeding up rather than slowing down over the past several billion years. This acceleration requires the existence of some form of energy that exerts repulsive rather than attractive gravitational effects, overwhelming the attractive gravitational forces generated by all visible matter in galaxies, stars, and gas clouds. The energy density required to drive cosmic acceleration must dominate the universe's total energy budget, contributing roughly 70% of all energy and matter combined. Yet this dark energy remains completely invisible to all forms of electromagnetic observation. The physical nature of dark energy presents profound puzzles that challenge fundamental understanding of space, time, and gravitational theory. Unlike ordinary matter and energy, which become diluted as cosmic expansion increases the volume of space, dark energy maintains constant density as the universe expands. This property means that dark energy's total contribution to cosmic dynamics grows continuously as expansion creates larger volumes of space, eventually overwhelming all other forms of energy and matter. Einstein's cosmological constant provides one theoretical framework for understanding dark energy, representing the energy density of empty space itself. According to quantum field theory, even completely empty vacuum contains zero-point fluctuations of all possible particle fields, contributing a uniform energy density to every region of space regardless of its matter content. This vacuum energy would naturally maintain constant density during cosmic expansion while exerting repulsive gravitational effects that accelerate expansion. Yet, the observed dark energy density falls far short of theoretical predictions for vacuum energy based on quantum field theory calculations. Summing the zero-point energies of all known particle fields yields vacuum energy densities larger than observed dark energy by factors of 10 circumflex 120, the largest discrepancy between theory and observation in the history of physics. Either quantum field theory fundamentally misunderstands vacuum energy, or some unknown mechanism cancels vacuum energy contributions with extraordinary precision. Alternative dark energy models propose that cosmic acceleration results from evolving scalar fields that change their energy densities over cosmic time, creating time-variable effects that might eventually reverse cosmic acceleration or drive it toward even more extreme values. These quintessence models avoid the vacuum energy problem by attributing dark energy to dynamical fields rather than static space properties, but they require new fundamental physics beyond the standard model of particle interactions. The measurement of cosmic acceleration also reveals that dark energy's dominance represents a relatively recent development in cosmic history. During early cosmic epochs, when matter densities were much higher due to smaller cosmic volumes, gravitational attraction from ordinary and dark matter overwhelmed dark energy's repulsive effects. Cosmic expansion decelerated throughout most of cosmic history, only beginning to accelerate approximately 5 billion years ago when decreasing matter densities allowed dark energy to dominate cosmic dynamics. This transition from decelerated to accelerated expansion occurs at roughly the same cosmic epoch when solar system formation began, suggesting possible connections between cosmic acceleration and the specific environmental conditions that allowed planetary formation and biological evolution. If cosmic acceleration had begun earlier or proceeded more rapidly, galactic structure formation might have been disrupted before star formation could proceed efficiently enough to synthesize heavy elements necessary for planetary development. The future evolution of cosmic acceleration depends critically on dark energy's specific properties, which remain almost completely unknown despite its dominant influence on cosmic dynamics. If dark energy maintains constant density, as current observations suggest, cosmic expansion will continue accelerating indefinitely, eventually carrying distant galaxies beyond observable horizons and leaving our local galactic group isolated within an expanding bubble of empty space. More extreme dark energy models predict that acceleration might increase over time, leading to Big Rip scenarios where expansion eventually becomes so rapid that it overcomes gravitational binding within galaxies, stellar systems, and ultimately, atomic nuclei themselves. Such outcomes would terminate cosmic evolution within finite time by disrupting all gravitationally bound structures through runaway expansion. Alternatively, dark energy might decay or reverse its effects over cosmic time, potentially leading to eventual cosmic contraction that reverses current expansion and drives the universe toward a big crunch collapse. These scenarios require dark energy properties that differ fundamentally from cosmological constant models, involving dynamical evolution that remains completely speculative without additional observational constraints. The discovery of cosmic acceleration also raises profound questions about the relationship between cosmic evolution and the physical laws that govern space and time. If dark energy represents a fundamental property of space itself, then the geometry and dynamics of space-time possess characteristics that exceed current understanding of gravitational theory and quantum mechanics. The universe operates according to principles that remain mysterious despite their dominant influence on cosmic fate. The observational study of dark energy requires extending supernova observations to even greater distances and developing alternative measurement techniques that can probe cosmic expansion across different cosmic epochs, gravitational lensing by dark energy concentrations, large-scale galaxy clustering patterns, and cosmic microwave background radiation all provide independent approaches for measuring dark energy properties and constraining theoretical models, yet each observational technique faces significant technical challenges that push against current astronomical capabilities. Distant supernova observations require space-based telescopes capable of detecting extremely faint objects while maintaining photometric precision sufficient for reliable distance measurements. Gravitational lensing studies demand wide-field surveys that can map galaxy shapes across enormous sky areas with sufficient statistical precision to detect subtle dark energy effects. The theoretical understanding of dark energy also requires advances in fundamental physics that connect gravitational theory, quantum mechanics, and particle physics in ways not yet achieved through current theoretical frameworks. The energy scales and density regimes relevant to dark energy span ranges from quantum field theory to cosmic structure formation, demanding unified theoretical approaches that remain beyond current scientific capabilities. Throughout 1998 and beyond, dark energy continues driving cosmic acceleration at rates that will eventually separate galactic clusters beyond mutual gravitational influence. While the fundamental nature of this cosmic acceleration remains as mysterious as any phenomenon in the history of science, the universe expands, vast and accelerating, following dynamics governed by energy forms that dominate cosmic evolution, yet remain completely invisible to all known observational techniques. Meanwhile, the systematic study of cosmic acceleration awaits technological advances in space-based astronomy and theoretical developments in fundamental physics that will gradually reveal the nature of dark energy and its ultimate influence on cosmic fate. The universe accelerates its expansion through mechanisms not yet understood, revealing its most profound characteristics to observers equipped with sufficient observational precision and theoretical sophistication to recognize the signatures of invisible energy that shapes cosmic destiny. The year drifts through 1967, and John Wheeler sits in his office at Princeton University, contemplating the mathematical implications of Einstein's general relativity theory when applied to stellar objects so massive and compact that their gravitational fields prevent even light from escaping their surfaces. Wheeler coins the term black hole to describe these theoretical objects, replacing the cumbersome phrase gravitationally completely collapsed object with terminology that captures the essential characteristic of regions in space from which nothing can return once it crosses a critical boundary. The mathematical foundation for black hole physics extends directly from Carl Schwarzschild's 1916 solution to Einstein's field equations, which describes the gravitational field surrounding any spherically symmetric mass. Schwarzschild's calculations reveal that sufficiently compact masses create regions of space-time so severely curved that the usual concepts of space and time break down entirely. At a critical radius, now called the Schwarzschild radius, the curvature becomes so extreme that space and time exchange roles, creating an event horizon beyond which causality itself prevents communication with the external universe. For any given mass, the Schwarzschild radius defines the boundary within which gravitational collapse becomes irreversible. A stellar mass compressed within its Schwarzschild radius creates a black hole from which no material object, electromagnetic radiation, or information of any kind can escape to reach external observers. The escape velocity from the Schwarzschild radius equals the speed of light, making escape physically impossible according to relativistic constraints on maximum achievable velocities. The formation of stellar mass black holes requires extreme conditions that push matter beyond all known physical resistance mechanisms. Normal stellar structure depends on pressure forces generated through nuclear fusion, electron degeneracy, or neutron degeneracy that balance gravitational compression and maintain stellar equilibrium across billions of years. But gravitational forces from sufficiently massive stars can overwhelm all possible pressure sources, leading to catastrophic collapse that crushes matter to infinite density within infinitesimal volumes. This collapse process occurs when massive stars exhaust their nuclear fuel and can no longer generate sufficient pressure to support their own gravitational weight. Without nuclear burning to maintain internal heat and pressure, gravitational forces compress stellar cores beyond white dwarf and neutron star configurations toward densities that exceed nuclear matter by enormous factors. Once collapse begins, no known physical process can halt compression before matter reaches the theoretical singularity predicted by general relativity. Yet the observational detection of black holes presents seemingly insurmountable challenges, since by definition these objects emit no electromagnetic radiation that could reveal their presence through conventional astronomical techniques. Black holes can be detected only through their gravitational effects on nearby matter, orbital motion of companion stars, accretion of gas that heats to X-ray emission temperatures before crossing the event horizon, or gravitational lensing of background light sources. The search for black hole candidates focuses primarily on X-ray binary systems where compact objects orbit normal stars while accreting matter through gravitational tidal forces. As gas spirals toward the compact object, friction and compression heat the material to temperatures exceeding 10 million degrees, creating intense X-ray emission from the accretion disk before matter disappears beyond the event horizon. The X-ray characteristics and orbital dynamics can reveal whether the compact object possesses mass and size consistent with black hole predictions. Cygnus X1 emerges as the first compelling black hole candidate through systematic X-ray and optical observations that reveal a massive, compact object orbiting a blue supergiant star. The system's orbital characteristics indicate that the compact object contains approximately 10 solar masses compressed within a region smaller than neutron star configurations can accommodate. No known physical mechanism except black hole formation can create objects with such extreme mass-to-size ratios. The X-ray emission from Cygnus X1 shows rapid variability on timescales of milliseconds, indicating that the emission region cannot exceed light travel distances corresponding to these variation periods. This constraint forces X-ray generation into volumes comparable to stellar radii, yet containing masses 10 times greater than our Sun. The combination of extreme compactness with high mass provides strong evidence for black hole physics operating within observable astronomical systems. More exotic black hole candidates include supermassive objects that might exist within galactic nuclei containing millions or billions of stellar masses within regions comparable to solar system dimensions. These galactic-scale black holes could power quasar phenomena through gravitational energy release as matter spirals into supermassive event horizons, converting gravitational potential energy into electromagnetic radiation with efficiencies far exceeding nuclear fusion processes. The physics of matter approaching black hole event horizons creates fascinating theoretical puzzles about information preservation and thermodynamic properties of gravitational systems. According to general relativity, outside observers never see objects actually cross event horizons. Instead, gravitational time dilation causes infalling matter to appear increasingly redshifted and time-dilated until it fades beyond detectability while remaining perpetually frozen at the horizon boundary. This temporal paradox raises profound questions about black hole thermodynamics and the ultimate fate of information that approaches event horizons. If black holes eventually evaporate through quantum radiation processes predicted by Stephen Hawking's theoretical calculations, what happens to the information content of matter that appeared to remain frozen at event horizon boundaries? The reconciliation of general relativity with quantum mechanics requires theoretical frameworks not yet developed. Black hole thermodynamics also predicts that these objects possess temperatures and entropies determined by their surface areas rather than their volumes, suggesting deep connections between gravitational physics and information theory. The entropy of a black hole grows in proportion to its event horizon area, implying that information storage within gravitational systems follows principles completely different from ordinary thermodynamic systems. The detection of gravitational waves from black hole mergers represents another potential avenue for studying black hole physics through entirely different observational techniques. When two black holes spiral together and merge, they should create ripples in space-time itself that propagate at light speed and carry information about black hole masses, spins, and merger dynamics. These gravitational wave signals would provide direct evidence for black hole existence while testing general relativity under extreme gravitational conditions. Yet gravitational wave detection requires technological precision that exceeds current engineering capabilities by enormous factors. The anticipated gravitational wave amplitudes from black hole mergers would distort space itself by fractions smaller than nuclear dimensions, demanding laser interferometry systems capable of measuring length changes smaller than 10 circumflex 18 meters across kilometer-scale detector arms. The theoretical study of black hole physics also reveals connections between gravitational theory and quantum mechanics that suggest fundamental limitations on physical knowledge itself. The combination of general relativity and quantum mechanics predicts that black holes should emit thermal radiation through quantum fluctuations near event horizons, causing black holes to evaporate slowly over timescales that exceed the current age of the universe by enormous factors for stellar mass objects. This Hawking radiation process implies that black holes possess finite lifetimes determined by their masses, with smaller black holes evaporating faster than larger ones. Primordial black holes formed during early cosmic epochs might be completing their evaporation processes in the current universe, creating detectable signatures through gamma-ray emission as their event horizons shrink toward quantum dimensions. The formation of black holes during cosmic evolution also affects large-scale structure development and galactic evolution through gravitational feedback processes that remain poorly understood. Supermassive black holes within galactic nuclei might regulate star formation rates through energy injection that heats galactic gas beyond star formation thresholds, creating feedback loops that connect black hole growth with galactic stellar populations. Throughout 1967 and beyond, black holes continue their silent gravitational influence on cosmic structure while remaining completely invisible to electromagnetic observation except through their effects on nearby matter. These gravitational monuments to extreme physics operate according to principles that combine general relativity and quantum mechanics in ways not yet understood, revealing the universe's capacity for creating physical conditions that exceed terrestrial experience by factors that challenge human comprehension. The systematic study of black hole physics awaits technological advances in X-ray astronomy, gravitational wave detection, and theoretical developments in quantum gravity that will gradually reveal the physical processes operating within regions where space and time exchange roles and causality itself becomes subject to gravitational control. Black holes exist, vast and patient, following mathematical laws that govern space-time curvature while concealing their secrets behind event horizons that prevent direct observation of their most extreme physical characteristics. The year settles into 1972, and Alaa Tumra sits before primitive computer terminals at MIT. running gravitational simulation codes that model what happens when two spiral galaxies approach each other across cosmic space and merge through gravitational attraction. His computational experiments reveal that galactic collisions, rather than destroying spiral structure through chaotic disruption, create entirely new galactic architectures through orderly gravitational choreography that unfolds across hundreds of millions of years. The universe, it emerges, builds its largest structures through cosmic dance rather than cosmic violence. Toomer's simulations begin with simplified models representing each galaxy as a collection of mass points subject to mutual gravitational attraction according to Newton's inverse square law. The computational requirements push against available computer capabilities, forcing him to reduce galactic complexity to perhaps 1,000 individual particles rather than the billions of stars that populate real galactic systems. Yet even these simplified models reveal gravitational interactions far more complex and beautiful than anyone has previously imagined. When two model spiral galaxies approach each other with appropriate relative velocities and impact parameters, their gravitational fields begin distorting each other's structure long before direct contact occurs. Tidal forces stretch galactic disks into elongated configurations, while differential gravitational acceleration creates streams of stars that flow between the approaching systems. These tidal streams preserve orbital energy and angular momentum through gravitational interactions, creating temporary bridges of stellar material spanning hundreds of thousands of light-years between galactic cores. The most striking feature of galactic merger simulations involves the formation of spectacular tidal tails, long streams of stars pulled from galactic disks during close gravitational encounters. These stellar streams extend far beyond original galactic boundaries, creating temporary cosmic artifacts that span millions of light-years while maintaining coherent dynamical structure determined by the orbital mechanics of galactic interaction. The tidal tails sweep through space like cosmic brushstrokes, tracing gravitational force patterns invisible to direct observation. As galactic merger processes continue, computational models reveal that initial spiral structures disappear entirely, replaced by elliptical configurations that bear no resemblance to either original spiral galaxy. The merged system settles into gravitational equilibrium with stellar orbits randomly oriented rather than confined to rotating disk structures. Spiral arms vanish, galactic rotation slows dramatically, and stellar populations redistribute throughout three-dimensional ellipsoidal volumes rather than thin disk configurations. This transformation from spiral to elliptical morphology through gravitational merger provides the first theoretical framework for understanding the diversity of galactic types observed throughout the universe. Rather than representing different formation mechanisms or evolutionary pathways, spiral and elliptical galaxies might represent different stages in gravitational evolution determined by merger histories. Galaxies that avoided major merger events maintain spiral structure, while those that experienced significant collisions evolved into elliptical configurations. The timescales involved in galactic merger processes span hundreds of millions of years, comparable to biological evolution timescales on planetary surfaces. Yet brief by cosmic standards, during merger evolution, stellar formation rates increase dramatically as gas clouds collide and compress, triggering bursts of star formation that create young stellar populations throughout merged systems. These starbursts temporarily increase galactic luminosity by factors of 10 or more, creating some of the brightest galactic systems observable at cosmological distances. Yet, the fate of planetary systems during galactic mergers remains entirely speculative, since computational models cannot track individual stellar systems or planetary orbits during gravitational disruption events. Stars themselves rarely collide during galactic mergers due to enormous separation distances between individual stellar objects, but their orbital trajectories change dramatically as galactic gravitational potentials evolve during merger processes. Planetary systems might survive gravitational disruption, or they might be scattered into galactic halos through close stellar encounters. The observational testing of galactic merger theory requires identifying galaxy pairs in various stages of gravitational interaction, then measuring their structural and kinematic properties to compare with theoretical predictions. Galaxies in early merger stages should show tidal distortions and stellar streams extending between approaching systems, while galaxies in late merger phases should display disturbed morphologies that deviate from normal spiral or elliptical configurations. The antennae galaxies provide the most spectacular example of ongoing galactic merger, displaying prominent tidal tails extending far beyond their main bodies while showing intense star formation. Throughout regions where gas clouds collide during gravitational interaction, radio observations reveal complex velocity patterns indicating orbital motion around multiple gravitational centers, confirming that two separate galactic systems are indeed merging through gravitational attraction. Similar merger signatures appear in numerous galactic systems throughout the observable universe, suggesting that galactic collisions represent common rather than exceptional events in cosmic evolution. The frequency of observable merger features implies that most galaxies experience significant gravitational interactions during their evolutionary histories, with merger processes playing fundamental roles in determining final galactic properties and morphological classifications. The computational study of galactic mergers also reveals unexpected connections between supermassive black holes and galactic evolution that emerge naturally from gravitational dynamics during collision events. When two galaxies merge, their central black holes eventually spiral together through gravitational wave emission, creating binary black hole systems that might power quasar phenomena through enhanced accretion during orbital decay phases. This connection between galactic mergers and active galactic nuclei provides potential explanations for quasar evolution and the observed decline in quasar activity since early cosmic epochs. If quasars result from enhanced black hole accretion during galactic merger events, then quasar frequency should correlate with cosmic merger rates, which presumably decreased as cosmic expansion reduced galactic encounter frequencies throughout cosmic history. The gravitational wave emission from merging supermassive black holes creates another observational signature of ancient galactic merger events that might be detectable through future gravitational wave astronomy missions. These gravitational waves carry precise information about black hole masses and merger dynamics across cosmic distances, providing direct observational access to galactic merger processes that occurred billions of years ago. Advanced computational simulations reveal additional complexity in galactic merger outcomes that depends critically on initial conditions, including galactic masses, gas content, orbital parameters, and encounter geometries. Head-on collisions create different merger products than glancing encounters, while gas-rich galaxies evolve differently than gas-poor systems during gravitational interaction. The diversity of merger outcomes helps explain the complex variety of galactic morphologies observed throughout cosmic surveys. The role of dark matter in galactic merger processes adds further computational complexity that challenges current simulation capabilities. Dark matter halos surrounding visible galaxies contain most galactic mass and determine large-scale gravitational dynamics during merger events. Yet, dark matter particle interactions remain poorly understood and difficult to model accurately. Simplified dark matter models might miss important dynamical effects that influence merger outcomes and final galactic properties. Environmental effects also influence galactic merger processes in ways that depend on local cosmic architecture and the presence of additional gravitational perturbations from nearby galactic systems. Galaxy clusters create tidal environments that can accelerate or inhibit merger processes, while cosmic filaments channel galactic interactions along preferred orientations determined by large-scale structure formation. The ultimate fate of merged galactic systems depends on cosmic expansion rates and dark energy evolution that will determine whether merged galaxies remain gravitationally bound or eventually separate through accelerating cosmic expansion. If dark energy continues driving cosmic acceleration, currently merged systems might represent temporary gravitational associations that will eventually dissolve as cosmic expansion overwhelms gravitational binding. Throughout 1972 and beyond, galactic merger processes continue their slow gravitational choreography across cosmic space, building elliptical galaxies through spiral galaxy collisions while triggering starbursts and black hole activity that can be observed across billions of light-years. The universe constructs its architectural diversity through gravitational interactions that unfold across timescales spanning hundreds of millions of years, revealing cosmic evolution as a dynamic, ongoing process rather than static structural arrangement. The computational study of galactic evolution awaits advances in computer technology and theoretical understanding of dark matter physics that will enable more realistic simulations of galactic merger processes across cosmic time. Galaxies dance their gravitational ballet, vast and patient, following mathematical laws that govern orbital mechanics while gradually building cosmic structure through merger processes that transform galactic morphology across cosmic evolution. The year moves through 1986, and Margaret Geller stands before maps of galaxy positions that reveal patterns so unexpected and geometrically regular that they challenge every assumption about cosmic architecture and large-scale structure formation. Her systematic survey of galaxy redshifts, conducted with John Huckra using the Multiple Mirror Telescope, has produced three-dimensional maps showing that galaxies do not distribute randomly throughout space as cosmological theory predicts, but instead organize themselves into vast networks of filaments, walls, and voids that span hundreds of millions of light-years. The mapping technique requires measuring precise redshifts for thousands of individual galaxies, then converting these recession velocities into distance estimates using Hubble's expansion relationship, when plotted in three-dimensional coordinates that account for both angular position and distance. Galaxy distributions reveal large-scale structure that resembles biological tissue more than random point distributions. Galaxies cluster along thin filamentary chains that intersect at dense nodes, creating cosmic networks separated by enormous empty regions almost devoid of galactic material. The most striking feature of these cosmic maps involves the Great Wall, a coherent structure of galaxies extending more than 500 million light-years across space, yet only 15 million light-years thick. This cosmic wall contains thousands of individual galaxies organized into a sheet-like configuration that curves gently through space while maintaining remarkable structural coherence across distances comparable to significant fractions of the observable universe. No theoretical mechanism predicted structures of such enormous scale and geometric regularity. The existence of cosmic walls and filaments conflicts with standard cosmological models that assume matter distributed nearly uniformly throughout space on scales larger than individual galaxy clusters. If cosmic matter began in nearly smooth configurations as cosmic microwave background observations suggest, then gravitational instability should have created roughly spherical mass concentrations rather than the sheet-like and filamentary structures revealed through galaxy mapping. The cosmic web topology suggests gravitational evolution far more complex than simple spherical collapse models predict. Equally puzzling, the vast empty regions between cosmic filaments, cosmic voids spanning 100 to 300 million light-years in diameter, contain almost no galaxies despite representing majority volumes of cosmic space. These voids appear inconsistent with uniform matter distribution assumptions, since even small initial density fluctuations should have grown into detectable galactic concentrations through gravitational amplification over cosmic evolution timescales. The near emptiness of cosmic voids suggests that structure formation processes actively emptied these regions while concentrating matter into surrounding filaments. The scale of cosmic structure also creates temporal paradoxes that challenge understanding of cosmic evolution and gravitational dynamics. Light requires hundreds of millions of years to travel across observed cosmic filaments. Yet these structures maintain coherent organization despite lacking obvious physical mechanisms for coordinating structure formation across such enormous scales. Gravitational influences propagate at light speed, making it difficult to understand how cosmic matter could organize itself into structures larger than light travel distances since cosmic structure formation began. Computer simulations of cosmic structure formation reveal that cold dark matter, hypothetical particles that interact only gravitationally, can create filamentary networks resembling observed cosmic architecture through hierarchical gravitational clustering. In these simulations, dark matter begins collapsing into small-scale structures that gradually merge into progressively larger systems, eventually creating cosmic webs with topological properties similar to galaxy survey observations. Yet these dark matter simulations require specific assumptions about dark matter particle properties, cosmological parameters, and initial condition spectra that remain largely unconstrained by independent observations. The simulations also predict detailed structure characteristics that prove difficult to test through galaxy surveys, limited by observational selection effects and finite survey volumes. The agreement between simulated and observed cosmic structure remains qualitative rather than quantitative. The formation of cosmic voids presents particularly challenging theoretical problems for gravitational structure formation models. If cosmic matter began in nearly uniform distributions with small random fluctuations, gravitational instability should have amplified density contrasts while preserving total matter content within any given spatial region. Creating genuine voids requires physical mechanisms that can transport matter from underdense regions into surrounding overdense areas across scales larger than typical gravitational influence. Possible void formation mechanisms include explosive feedback from early stellar populations that could drive galactic material from low-density environments into higher-density regions, or hydrodynamical processes involving cosmic gas flows that preferentially channel matter along gravitational potential gradients. These mechanisms require coordination between stellar formation, galactic evolution, and large-scale gravitational dynamics across cosmic evolution timescales. The observational mapping of cosmic structure also reveals systematic patterns in galaxy velocities that suggest large-scale gravitational flows extending far beyond individual galactic neighborhoods. Galaxies appear to stream toward massive structure concentrations while flowing away from cosmic voids, creating velocity fields that span hundreds of millions of light-years. These peculiar velocity patterns indicate gravitational influences from matter distributions extending far beyond the survey boundaries used to map visible cosmic structure. The Great Attractor represents one example of these large-scale gravitational anomalies, an enormous mass concentration that appears to draw galaxies from vast surrounding regions toward a location obscured by dust clouds within our own galactic plane. The gravitational influence of this hidden mass concentration affects galactic motion across distances exceeding 200 million light-years, yet its precise location and total mass remain uncertain due to observational obscuration. These large-scale velocity flows suggest that cosmic structure extends beyond currently mapped regions, with mass concentrations and void patterns that influence galactic dynamics across even larger scales than direct galaxy surveys can trace. The cosmic web topology might represent only the visible portion of gravitational architecture that continues across scales approaching the observable universe boundaries. The relationship between cosmic structure and galaxy formation also reveals systematic correlations that suggest environmental effects play crucial roles in determining galactic properties and evolutionary histories. Galaxies within cosmic filaments show different morphological, stellar population, and star formation characteristics compared to galaxies in cosmic voids, indicating that large-scale environment influences galactic evolution through mechanisms that remain poorly understood. Environmental effects on galaxy formation might involve tidal interactions with large-scale gravitational fields, variations in cosmic gas density that affect stellar formation processes, or merger frequency differences between high-density and low-density cosmic environments. These environmental influences could create systematic biases in galaxy samples that complicate attempts to understand intrinsic galactic evolution through observational surveys. The cosmic web structure also affects cosmic evolution through its influence on intergalactic gas dynamics and cosmic reionization processes. Gas flow patterns within cosmic filaments might channel primordial material toward galactic formation sites while creating shock heating that affects subsequent stellar formation rates. The topology of cosmic structure determines how radiation from early stellar populations propagates through intergalactic space during cosmic reionization epochs. Advanced galaxy surveys extending to higher redshifts reveal cosmic structure evolution across cosmic time, showing that filamentary patterns existed during earlier cosmic epochs when the universe was significantly younger and denser. These observations suggest that cosmic web formation began relatively early in cosmic history, perhaps driven by dark matter clustering that preceded visible galaxy formation by hundreds of millions of years. The future evolution of cosmic structure depends critically on dark energy properties and cosmic expansion rates that will determine whether current filamentary patterns persist or gradually dissolve through accelerating expansion. If cosmic acceleration continues indefinitely, cosmic filaments might eventually stretch beyond gravitational binding thresholds, isolating individual galaxy clusters within expanding voids that grow to encompass most cosmic volume. Throughout 1986 and beyond, cosmic structure continues its gravitational evolution across scales spanning hundreds of millions of light-years, organizing galaxies into filamentary networks while creating vast empty voids that contain almost no visible matter. The universe reveals its large-scale architecture through galaxy surveys that map cosmic structure extending far beyond any previously imagined scale of gravitational organization. The systematic mapping of cosmic structure awaits technological advances in automated galaxy survey techniques and theoretical developments in structure formation physics that will gradually reveal the gravitational and hydrodynamical processes responsible for cosmic web formation. The cosmic web evolves, vast and patient, following mathematical laws that govern gravitational clustering while organizing cosmic matter into architectural patterns that resemble neural networks more than random matter distributions. The year drifts through 2003, and teams of astronomers gather around computer screens displaying the first deep field images from the newly launched Spitzer Space Telescope. Its infrared detectors capturing light from galaxies so distant that their luminosity began its journey toward Earth when the universe was less than 1 billion years old. These ancient galaxies appear as they existed during cosmic dawn, the epoch when first-generation stars ignited within primordial gas clouds and began synthesizing heavy elements that would eventually make planets and life possible throughout cosmic evolution. The infrared observations pierce through cosmic dust clouds that block optical light from early galactic epochs, revealing stellar populations and galactic structures invisible to conventional telescopic techniques. At these enormous distances, corresponding to redshifts exceeding 6 or 7, the expansion of cosmic space has stretched ultraviolet and visible light from early stellar populations into infrared wavelengths detectable only through space-based instruments operating beyond Earth's atmospheric absorption. These cosmic time machines reveal galactic architecture as it existed when cosmic structure was just beginning to emerge from primordial darkness. The galaxies observed at such extreme distances appear dramatically different from their modern counterparts, displaying irregular morphologies, intense star formation rates, and compact sizes that suggest cosmic evolution has fundamentally transformed galactic properties over billions of years. These early systems contained stellar populations with chemical compositions dominated by hydrogen and helium, the primordial elements synthesized during cosmic nucleosynthesis, with heavy element abundances far below those observed in contemporary galactic environments. Yet even these ancient galaxies show evidence of previous stellar generations that lived, evolved, and dispersed heavy elements through supernova explosions before the galaxies currently observed began forming their stellar populations. Carbon, nitrogen, oxygen, and iron signatures detected through spectroscopic analysis indicate that stellar nucleosynthesis had already proceeded through multiple cycles by the time these distant galaxies accumulated sufficient matter to become visible across cosmic space. The universe reveals its stellar chemistry as a cumulative process extending back toward cosmic origins. The star formation rates inferred from infrared luminosity measurements indicate that early galaxies converted gas into stars far more efficiently than modern galactic systems, creating stellar populations at rates exceeding contemporary star formation by factors of 10 to 100. This enhanced star formation efficiency suggests that physical conditions during early cosmic epochs, gas densities, temperature distributions, turbulent velocities, differed significantly from those observed in local galactic environments. The morphological properties of high redshift galaxies also reveal cosmic evolution patterns that connect early irregular systems with the organized spiral and elliptical structures observed in the contemporary universe. Early galaxies appear fragmented and asymmetric, lacking the geometric regularity that characterizes mature galactic systems. These morphological differences suggest that galactic evolution involves gradual organization of chaotic initial configurations into stable rotating disks or relaxed ellipsoidal distributions. Computer simulations of cosmic structure formation predict that early galactic systems should appear smaller and more compact than modern galaxies due to the higher cosmic densities and different dark matter clustering properties that characterized earlier cosmic epochs. The observed compactness of high redshift galaxies confirms these theoretical predictions while revealing that galactic evolution includes systematic size growth through accretion, mergers, and internal dynamical evolution. The chemical evolution revealed through high redshift galaxy observations traces the cosmic enrichment of heavy elements from initial abundances near zero to the complex chemical compositions observed in contemporary stellar populations. Each generation of massive stars synthesizes elements heavier than helium through nuclear fusion processes, then disperses these products throughout galactic environments through supernova explosions that enrich surrounding gas clouds with processed stellar material. This cosmic chemical evolution proceeds at different rates within different galactic environments, creating chemical abundance patterns that depend on stellar formation histories, galactic masses, and environmental conditions that vary across cosmic space and time. The chemical signatures observed in distant galaxies provide fossil records of stellar nucleosynthesis that reveal how cosmic chemistry evolved from primordial simplicity toward the complex elemental compositions required for planetary formation and biological development. The detection of supermassive black holes within high redshift galaxies presents additional puzzles about cosmic evolution and the relationship between galactic and black hole growth during early cosmic epochs. Some distant galaxies show evidence of active galactic nuclei powered by black holes containing millions of stellar masses. Yet these massive objects exist when the universe was too young for conventional black hole growth mechanisms to accumulate such enormous masses through stellar formation and accretion processes. The presence of supermassive black holes in early cosmic epochs suggests that black hole formation and growth preceded galactic assembly, perhaps through direct collapse of primordial gas clouds or through seed black holes formed during cosmic structure formation. The coevolution of galaxies and their central black holes appears to begin during cosmic dawn, creating feedback relationships that influence both galactic star formation and black hole accretion throughout subsequent cosmic evolution. Gravitational lensing by intervening galactic clusters allows astronomers to observe even more distant and intrinsically fainter galaxies through natural telescopic magnification that amplifies light from background sources. These gravitationally lensed systems reveal galactic populations extending to redshifts approaching 10, corresponding to cosmic epochs when the universe was less than 500 million years old and galactic formation was just beginning throughout cosmic space. The discovery of galaxies at such extreme distances approaches observational limits imposed by cosmic reionization, the epoch when first-generation stars produce sufficient ultraviolet radiation to ionize hydrogen throughout intergalactic space. Before reionization, neutral hydrogen absorbs ultraviolet light from stellar sources, making galaxies invisible to optical and near-infrared observation regardless of instrumental sensitivity. The cosmic dark ages preceding reionization remain largely inaccessible to direct galactic observation, yet indirect evidence suggests that stellar formation began even earlier than currently observable galaxies indicate, perhaps within 100 to 200 million years after cosmic recombination, when temperatures first dropped sufficiently for neutral hydrogen formation. These earliest stellar populations, population 3 stars formed from pure primordial gas, should differ dramatically from all subsequently observed stellar types, containing no heavy elements and achieving masses far exceeding those of contemporary star formation processes. The search for population 3 stellar signatures requires detecting their influence on cosmic reionization, chemical enrichment, and background radiation rather than observing the stars directly. These primordial stellar populations should produce characteristic spectral signatures in cosmic microwave background radiation, create specific heavy element abundance patterns in subsequent stellar generations, and contribute to cosmic reionization through intense ultraviolet emission from massive stellar surfaces. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spatial resolution, promises to extend galactic observations to even higher redshifts and reveal galactic formation processes during cosmic epochs currently inaccessible through existing observational techniques. Its observations might detect the transition from population 3 to population 2 stellar formation, map the cosmic reionization process through galactic survey statistics, and reveal how galactic properties evolved during the first billion years of cosmic history. The ultimate origin of cosmic structure formation traces back to quantum fluctuations during cosmic inflation, microscopic density variations that grew through gravitational amplification into the cosmic web architecture that guides galactic formation throughout cosmic evolution. These primordial fluctuations, imprinted as temperature variations in cosmic microwave background radiation, provide initial conditions for all subsequent structure formation including galactic assembly, stellar formation, and chemical evolution. The connection between quantum mechanics and cosmic architecture represents one of the most profound relationships in physical science, linking microscopic uncertainty principles with large-scale gravitational dynamics across cosmic evolution timescales. The galaxies observed through deep field surveys represent amplified quantum fluctuations that grew through gravitational clustering into stellar systems containing billions of individual stars and planetary systems. Throughout 2003 and beyond, ancient galaxies continue broadcasting their infrared emission across billions of light-years of expanding space, their photons carrying information about stellar formation, chemical evolution, and galactic assembly during cosmic epochs when the universe was young and structure formation was just beginning. Each infrared photon preserves evidence of cosmic dawn, revealing how complexity emerged from primordial simplicity through gravitational organization and stellar nucleosynthesis. The systematic study of cosmic dawn awaits further technological advances in space-based infrared astronomy and theoretical developments in structure formation physics that will gradually reveal the physical processes responsible for galactic formation during the universe's earliest epochs. Ancient galaxies shine across cosmic time, vast and patient, following gravitational laws that govern structure formation while revealing their secrets to observers equipped with sufficient technological sophistication to detect infrared emission from cosmic dawn. Meanwhile, the cosmic web continues its gravitational evolution, organizing matter into filamentary networks while galaxies form, evolve, and merge within this cosmic architecture across timescales spanning billions of years. The universe builds its complexity through patient gravitational processes that transform primordial fluctuations into the rich cosmic ecology observed throughout contemporary astronomical surveys. The observations drift through decades of accumulated starlight, each photon carrying its story across cosmic distances that exceed human comprehension. The universe reveals itself slowly, through patient accumulation of evidence that transforms misunderstanding into wonder, showing how cosmic architecture operates on scales and timescales that dwarf terrestrial experience, yet follow mathematical laws accessible to careful observation and theoretical analysis. From those first puzzling spiral nebulae observed through early telescopes to the cosmic web architecture mapped through galaxy surveys, humanity's conception of cosmic scale has expanded beyond any previous imagination. Galaxies that once appeared as nearby wisps of glowing gas now reveal themselves as entire cosmic cities containing billions of stars, scattered throughout space at distances measured in millions and billions of light-years, each one a complete universe in its own right. The cosmic expansion discovered through galactic recession measurements shows that space itself grows larger, carrying embedded galaxies away from each other at rates determined by their separation distances. Dark matter provides gravitational scaffolding for cosmic structure formation, while dark energy drives accelerating expansion that will eventually separate galactic clusters beyond mutual gravitational influence. Black holes concentrate matter into regions where space and time exchange roles, creating gravitational environments so extreme that causality itself prevents communication with external observers. Spiral patterns persist through galactic evolution not because matter rotates rigidly, but because density waves propagate through galactic disks, while individual stars and gas clouds orbit through spiral arms that maintain their structure through wave mechanics. Galactic mergers create elliptical systems from spiral precursors, building cosmic diversity through gravitational choreography that unfolds across hundreds of millions of years. Quasars shine with luminosities exceeding entire galaxies from emission regions smaller than solar systems, revealing energy conversion processes that approach theoretical efficiency limits. Radio astronomy reveals cosmic phenomena invisible to optical observation, while infrared telescopes peer through cosmic dust to observe galactic formation during cosmic dawn when the universe was young and structure formation was just beginning. The cosmic web organizes galaxies into filamentary networks separated by vast, empty voids, creating architecture that resembles biological tissue more than random matter distributions. Yet mysteries remain deeper than solutions, each discovery revealing new questions about cosmic evolution, dark matter physics, black hole thermodynamics, and the ultimate fate of accelerating expansion. The universe operates according to principles that exceed current theoretical understanding while revealing their effects through astronomical observation across cosmic space and time. Stars continue burning their nuclear fuel across galactic neighborhoods scattered throughout cosmic filaments, synthesizing heavy elements that will eventually become planets and perhaps life itself. Galaxies rotate against the cosmic background. Their spiral patterns maintained through processes that balance wave propagation with stellar orbital dynamics. Black holes accrete matter while warping space-time around event horizons that hide singularities from external observation. The cosmic expansion continues at accelerating rates driven by dark energy that dominates universal dynamics while remaining completely invisible to electromagnetic observation. Dark matter provides gravitational binding for cosmic structure while interacting only through gravitational forces that reveal its presence through orbital velocities and gravitational lensing effects. Cosmic time flows toward futures that depend on dark energy evolution, cosmic expansion rates, and the ultimate fate of accelerating space that might eventually overcome gravitational binding within galaxies themselves. The universe evolves. Vast and patient. Following mathematical laws that govern cosmic dynamics across scales and timescales that challenge human comprehension, yet yield their secrets to careful observation and theoretical analysis. Galactic light continues its journey across expanding space, carrying information about stellar formation, chemical evolution, and cosmic architecture toward observers who gradually develop sufficient technological and conceptual sophistication to recognize the significance of photons that travel billions of years to reach telescopic detection. The universe reveals itself through patient observation, showing how cosmic evolution transforms simple initial conditions into the complex structures observed throughout contemporary astronomical surveys. And in the quietness of cosmic space, galaxies continue their slow rotation and systematic recession, following gravitational dynamics and cosmic expansion while broadcasting electromagnetic radiation that encodes the history of cosmic evolution for observers equipped to decode the messages carried by starlight across vast distances and cosmic time. The cosmos rests in mathematical silence, waiting